We're gonna start in 1 minute. Please find time to have a seat. We're gonna start soon. Okay, folks, we're gonna get started. Good morning, everybody, and welcome to TEROS. Exciting to see all of you in person and after 2 years of Zoom fatigue. So, and I think this is first conference of mine that I see so many people outside UT. So, I think very exciting to meet all of you. So, my name is Yuke Zhu. I'm an assistant professor in the computer science department here at UT Austin. Here I direct the robot perception and learning lab. So I moved to Texas about 2 years ago. And before I moved here, my friends are telling me everything's big in Texas, right? And everything is getting bigger. So Texas has a economy of 1.8 trillion US dollars last year, and it's getting bigger. And the AI and the robotics technologies will likely have a transformative impact in shaping the future of this economy. And robotics researchers in Texas like us will likely play an indispensable role in taking this technological and scientific advances to the future, to the real world. So when chatting with my UT colleagues here doing robotics, and we're kind of surprised to realize how big the robotics community is in Texas. We have tons of amazing researchers doing a lot of great work in their home institute, but there's not really a centralized forum for us to just come hand with each other and cross-pollinate ideas and our latest and greatest research. So that's why we have TEROS, right? So as an event to put together all the robotics researchers all across Texas, and with the goal of eventually making this a regular annual event and maybe hosted in the future by different organizations and different universities. So that's really the goal to build this vibrant and ever-growing community for TEROS or Texas robotics researchers all across the state. So just want to tell you a little bit about TEROS participants today. We have researchers from 9 different Texas institutes, and we have about 100 plus attendees, and 93 of them are in person, 33 are online. This event also live stream on YouTube, so there's going to be people outside Texas watching the stream live. And we also have participants from 9 companies and the government and the industry research labs. And the majority group of the participants today are faculty and staff in robotics here in the state. And when we try to make connections with the robotic researchers, and we try to do our best in reaching out, so we end up this 9 participant in university for this year. This by no means is the full coverage of the robotics activity in this state, right? So, but we want to start from here and go bigger for future years. And today's event, we have 4 keynote speakers, 10 spotlights. We have 15 presentations, poster presentations in the atrium outside, and there's 2 networking sessions, and you can find the schedules online on our website. The most important to remember is there's a free coffee and free lunch provided by the event right outside the room. Okay, so and we have 2 keynote speakers. After that, we have coffee break in the morning, and then 1 coffee break in the afternoon, and lunches in the noon. Okay, and we have 4 amazing keynote speakers. Super excited to see Lydia Kavargi and Ken Fleischman, and they're going to talk in the morning, and Robin Murphy and Mary Hayhoe is going to talk in the afternoon. Just like the keynote speakers, we have a fantastic lineup for spotlight speakers, and they cover a broad range of robotic research from hardware design all the way to AI, intelligence, autonomy. Right? So there will be exciting talks. So with that, and I'm going to hand over to my co-organizer and dear colleague, and Joy Biswa, and who's going to talk about the details about the event.
Thank you, Jay. Hi everyone, my name is Joydeep Biswas. I'm an assistant professor in the computer science department, and my research is in perception and planning for long-term autonomy. Just a few notes about logistics. So if you want to use Wi-Fi, then you may use either UTGuest or EduRoam. Coffee and lunch will be outside this. On the third floor, you can get your drinks and food from the third floor atrium, and you can come down. The poster presentations will be held right outside here in the atrium. So we have set up the boards and easels over there. And just to point out, if you've been outside in the atrium, you've seen the spiraling staircase. That's what you use to go up to the third floor. And the space outside here is essentially the atrium. In the afternoon, we will be giving tours of Anahil's Gym, which is a newly renovated historical building, which is home to Texas Robotics, and you get to see all of the cool stuff that is going on there. And I just want to also give a shout out to the co-organizers, Michelle Carell, Yifeng Zhu, and Josh Hoffman. If you see them, please come say hi to them. Yifeng and Josh are PhD students working with Yuka and me. So please come say hi. We've been in touch over email. It's wonderful to put faces in connection with names. And we want to give a big shout out to Kwanzaa. We have free food and lunch and coffee. It was made possible by the generosity of Kwanzaa. So please stop by at the booths outside. Interestingly, when I was a graduate student, I told them that, I told them now that when I was a graduate student, I had to actually create class assignments based on their product. So, which is an interesting robot platform. So go take a look at the demo and say hi to them. Okay? And now I want to just briefly hand it over to Peter, who will tell us a little bit about Texas Robotics.
Thanks, Jody, and welcome everybody. It's great to have people from across the state, different universities, different industries and companies here joining us. I just want to take a minute before we launch into the program. First of all, to acknowledge, Jody just had up on the slide the organizers, but I think first of all, UK, as far as I know, I think you had the idea of doing this, and then Joydeep and UK together, two of our STAR assistant professors here, along with Josh and Yifeng and Michelle. So let's just take a second to give them a hand. And I really hope that this will become a tradition that will bring together people from across Texas who are interested in robotics. And we were excited to do this partly because we've recently launched here Texas Robotics at UT Austin. And it brings together our robotics students, faculty, researchers, and industry leaders to fuel the future of robotics at UT Austin and beyond. We do have, and we'll tell you about this, I'm not going to go into the details, it's all on the website. We have an education program that allows our graduate students to get credentialed in robotics on their transcripts. We do have, the core of it is really the faculty and the students on the research that's going on. We are really excited to, for those of you who haven't been here, to show off our new facility, Anahil's Gym. We've been working on it with the architects for the last several years, and it's fully opened less than a year ago, and really a fantastic facility that's for the first time allowing us to bring the robotics here that spans so many different departments all under one roof. And of course, an important part of this is also our industrial affiliates program. When I got to UT Austin back in 2002, I was sort of the third core roboticist. There was Ben Kuipers and Del Tessar were here, and then I joined. There were we were the only three who published in sort of ICRA and IROS. Those were the main conferences at the time. There wasn't RSS yet, and now we have across these four departments that you see on the left, we have 17 faculty who publish in ICRA, IROS, and RSS, and many hired over the last, just the last few years. And you'll hear from many of these faculty today. In spotlight type talks, we've decided to feature some of our assistant professors, some of the junior faculty, to complement some of the great speakers from outside of UT as well. And our research labs span a whole bunch of different areas here. I think it's really, really special that we do have I think we're about to lead into the invited talks, and to me, it was, we couldn't have an event like this without having our two out-of-town invited speakers who are really, I think, unquestionably two of the most prominent leading roboticists in this state, always have been. I've always looked up to the work of both of them. We have Lydia Kavraki, we have Robin Murphy. This event couldn't have, been the launch of a Texas robotics without the two of you here. So I'm really, really happy that you're able to be here and featured as keynote speakers. We also have two other keynote speakers from UT Austin who are outside of robotics to sort of, highlight some of the breadth of connections that robotics is engendering. And I'm really looking forward to the interactions we have today and to talking with all of you. And again, I hope this is the beginning of a very very rich tradition in our state over the coming years. So with that, I'll turn it back to, I don't know who's doing the introduction. All right. So.
Oh, you have an introduction.
Okay, so it's my great pleasure to introduce our first keynote speaker, Lydia Kavraki. Lydia Kavraki is a Noah Harding Professor of Computer Science and Bioengineering and the Director of the Ken Kennedy Institute at Rice University. Lydia's research is in enabling autonomy of robots working with and in service of human, and also AI applied to medicine. She has numerous contributions to the field. And as a young roboticist, I did learn about some of the most prominent contributions that she's had to the field, including the probabilistic roadmaps, which is interestingly an elegant and simple enough solution, which you could introduce to like an introductory robotics group, and it's still powerful enough that you can actually deploy them to the most complicated robotic systems, right? So that was really fascinating to me, and it's great to meet Lydia in person. Because of her many contributions to the field, she's been extremely well recognized. She has received many numerous awards, including the ACM Grace Murray Hopper Award, the ACM Athena Award, and the ACM AAAI Alan Newell Award. It's our pleasure to have Lydia present the keynote at the inaugural TEROS event. So I'll hand it over to
Thank you.
Lydia.
Thank you very much. Thank you for the introduction. Thank you for the invitation to be here. I'm really honored to be here, and I would like to thank the organizers for putting this together. And I hope it will be an opportunity for us to meet on a regular basis, exchange ideas, learn from each other. So my job here is to wake you up, and I intend to wake you up in the next half hour. So I will take this opportunity to talk about research that has been happening in my group over the last few years, and I will tell you about our successes and our challenges. To get started, I hope you will agree with me that recently we've seen robots do amazing specific tasks, right? And I'm showing to you here the AI hand, or the coordinated somersaults of the Boston Dynamics robots. Well, amazing, right? Automation has entered the warehouses, manufacturing is clear. But what is happening about our progress for robots for general tasks? There, I don't think we are that advanced. And one of the things that we would like to do in our group is work towards this goal. Being close to NASA, we've been inspired by their changes. So here is one example that inspired us. NASA built Robonaut 2, which you see in this picture here, in this slide here, to fetch cargo bags. I mean, it seems like an easy task, right? The cargo bags are stored in the space station. It's not a completely uncontrolled environment. It's a very controlled environment. This robot needs to fetch these cargo bags, and I think this problem is really archetypical of the complexities of commanding a robot. So using the amazing animations of my student Zach Kingston, who is here, you have this robot that needs to always hold on a handrail, right? Because it's up in the space and it will float if it's not holding to something, and get close to the cargo bag and remove the restraint and get the cargo bag and hold it tight because you don't want this cargo bag to fall out in space, and that would complete the task, okay? Well, great, all right, but how do you get all this done? And here's another example. You have a janitor robot. You want this robot to do things in some order, avoiding the black area because the demo is happening there. You want it to water the plant, clean the blackboard, turn off the copy maker, pick up the vacuum cleaner. I mean, your wish list here. And there may be temporal constraints, okay? Do this and then do that. How do we get closer to commanding robots doing a task like this? So we term this the task and motion planning problem. And in my opinion, it's a very nice platform, a very nice paradigm to think about meaningful interaction of perception, stated estimation, planning, and control. And I think it, at least for us, and I hope to convince you that this is a good idea, it has helped us a lot look at topics like learning, like formal methods and their role in robotics, symbolic reasoning and its role in robotics. And it also has given us, again, a framework to think about modularity, which in my opinion is something extremely important if we want robots for general tasks. I mean, what is modularity? How do we get to that? And to think about abstractions. And I will go and I will talk about abstractions and representations multiple times in my talk, because for us at least, they made a huge difference in whether we can do things or not do things. By working on these different issues, we get to a longer horizon tasks for robots and eventually to semi-autonomous or autonomous systems. Okay, so let me get started. Part one of my talk is I'll give you some background on my group. I'll talk about some recent projects, and I'll do that to show you where we are coming from. This is going to be a short part, about 5 minutes, and then I'm going to talk about task and motion planning, all right? So for the first part, as Joydeep said, we are a group that has a deep expertise in motion planning. So sampling-based planners for high-dimensional problems, besides the probabilistic roadmap, planners that work with geometric and dynamic constraints, with manifold constraints, uncertainty, sensing and action, multiple agents. And also, we are a group that supports a lot the design, implementation, and dissemination of software that will enable others to do things that have not been done by us or anybody else. So here is one of the posters that we will be presenting outside today is by Konstantinos Hamzas, who is sitting over there. And he is looking at how to use an experience database to guide high-dimensional planners for difficult tasks. So he stores, and he can tell you how, problems and experiences in a database that he retrieves once he's given a new problem instance, that is a new workspace, a new start and a goal, and uses the retrieved solution to find quickly a new solution. And he has worked a lot on retrieval functions, both manually and also he has learned retrieval functions. So talk to him. Another poster that we will be presenting today by Carlos Quintera Pena, who is also here, over there, working with Konstantinos and also with Professor Angel Carr at Rice, looks at the problem of human guidance in partially observable environments. So here is a case, we have a human that has a very good perception of the world she moves in. You can see it on the right, but the robot does not, as we all know, okay? It does not have the same kind of perception. So how do we use planning to propose, let's say, solutions to the human critiques these solutions, and then how do we use inverse reinforcement learning to converge to solutions that are robust for the environment where the human is working. To finish, the third part that I wanted to discuss is motion planning with manifold constraints. So Zach Kingston finished his PhD on this problem, inspired by the Robonaut problem. You can see here the robot turning a valve and pushing a door open. Okay, this is planning for a high-dimensional system, but with manifold constraints. Of course, there are many planners for this if you look at the literature, but what Zach did is that instead of changing the planners to work with manifold constraints, he endowed the search space with operations that support what sampling-place planners need. So you can take any sampling-place planner and use it to plan with manifold constraints, allowing you to choose the right planner for the right job. And once you understand, of course, how to plan with one manifold constraint, with one constraint, the question becomes, what if you have multiple of them? Okay, can you sequence them? Can you transition from constraint to constraint? Remember my discussion about modularity. And he actually showed, this animation here is a robot again, holding onto different handrails to get to its destination. But we don't tell the planner what to grasp or where to grasp it. Okay, the planner automatically decides that. And how does it decide that? I mean, this is a very structured reasoning, I would say, reasoning about modes and mode families. So each grasp of the handrail is a mode. All the possible grasps define a mode family. And Zach developed multimodal planning, finding paths that transition between modes within node families. And I hope this picture here shows you what is happening. You are moving on one manifold, let's say the purple manifold, until you can transition to another manifold, the green one, and follow the green manifold. But how to do that when you have many constraints is what Zach managed to do. So talk to him if you want during the breaks for this work. And as I said before, we really believe that we should be distributing our software and helping others work with the tools that we have developed and make them better. Really, the OMPL library, when it started, it was 5, 6, 7 maybe planners that we implemented, but we gave it a very good structure. And then it was really the community that contributed back. Right, contributed back to this the different assembly-based planners. So it's not only PRM and RRT, right? There are lots of different planners, and you need to understand which one to use. And this library implements all of them. So not from our work, but also contributions of many other people that we acknowledge in our webpage. It has more than 2,000 users. If you need planning for a high-dimensional system, check it out. And this is not the only thing that we are behind and we are trying to do our best to maintain. Planner Arena gives you a way to benchmark different motion planning algorithms, because as you all know, they don't have the same performance. And for the job that you have, you need to understand what planner to use. Hyperplan is a newer work. It's a framework for helping you select an algorithm, but also optimize the parameters of these algorithms. And those of you who have used the randomized algorithms know that if you don't tune a little bit the parameters, the performance is terrible. So here's some help on how to work with this. Motion Benchmaker helps generate benchmark problems and different data sets, which is becoming increasingly interesting now that we are talking about learning methods and how to use simulation. And finally, RoboFlex, which is really work again of John Kingston, is robot motion planning made easy with Move It Made Easy. Okay, this is a good title for what RoboFlex is. So these are things that we have developed over the years. We are trying to support. We would welcome your involvement. It is a community effort. It's not only our effort. All right. So I'm done with what I wanted to say about some background for our lab more during the poster session. Let me now talk about work on task and motion planning. So here is as an example. I have several cans on the table, and I want to instruct the robot to pick up the cans, to put them on this tray, and then to push the tray. So there is a number of discrete things that need to be decided. Okay, what do you do first? What do you do next? And then they need to be sequenced properly. The robot motions need to be planned. There is a discrete part, as you see, finding the task, and there is a continuous part, finding the motion, and then putting everything together. And in this case, we are just interested about one plan that will solve the problem. But in our work, we've actually, over several years, investigated how to find both paths for solving task and motion planning and policies for task and motion planning, and I will explain the difference between the two. We've used temporal logics for paths. We've used actually synthesis, formal methods, temporal logics for obtaining policies. I will start by discussing obtaining paths. As I described before, the task and motion planning problem, a discrete part, I mean some kind of a structure, a discrete structure on which you do the task planning, and then a continuous component. And yes, I know there are extremely good techniques for solving each of them, but the question here is how do you put them together? And how do you put them together is something that not only us, but several people over the years have tried to do. So I will tell you about some of our successes and some of the things that we find difficult. One of the approaches that has worked for us well when finding paths is the following. We keep some kind of a weighted graph structure, I will tell you how, that encodes the specification we use, in this case, in this slide, I have COSAFE LPL, linear temporal logic. I will tell you what this is. We have some abstraction of our robot and our environment. We encode this in our weighted graph. We find the task plan. We try to implement it using sampling-based motion algorithms. Doing only that is not enough. You have to have a feedback loop to, if you fail, I mean, what do you do? How do you adjust things? But this is a short description of how this work goes. So you have linear temporal logic propositions next until eventually is what is supported by COSAFE LTL. Why did we use COSAFE LTL? Because you can take it and transform it into a finite deterministic automaton. That in this automaton will encode all the valid prefixes of the linear temporal formula. So for computer scientists like me, this is wonderful, okay? This is great news. A structure I know how to manipulate that encodes my specification. And let me do also an abstraction of the environment. Now, if you have a mobile robot, the abstraction of the environment may be just adjacency, moving, you know, in a building, adjacency of rooms, but for a manipulator, it's something different. I'm not going to get into how you get abstractions from manipulators, an open problem, in my opinion. You take a cross product, and here is your graph, initially weighted with the same weights, but you start searching these graphs to find how to get from, let's say, your initial position to your final, which is always a double circle here. And if you succeed, that's great, you have found a solution. But if you don't succeed, you look for another way to get to your goal. But in the meantime, you keep memory of the fact that you did not succeed with the previous edge, okay, with this edge, and you weight your graph accordingly. And we found that this weighting is extremely important for getting complex things done. And we could, using sampling-based planners, get an estimate of the motion planning difficulty by finding how much progress was done in our space and projecting that to a lower dimension space. But there are many ways of doing that. For us, this paradigm worked well. And once it worked well, we said, wow, now we can put uncertainty in sensing, in action. Now we can put partially unknown environments. It's failing executions. Tianyang Pan, who is here, will be presenting a poster where he shows a case where you have a robot, let's say, manipulating these objects on the table, and the robot learns by the manipulation that it's doing. If these objects are not easy to grasp, okay, and it fails all the time, it keeps this information by sampling posterior transition probabilities, and it keeps this information in an MDP, and does the task and motion planning with this MDP, converging to more robust solutions if it's given the same scenario again and again. All right. But what I'm going to do in the last part of this talk is discuss what happens with task and motion planning when you have an uncontrollable agent. And this is the second part of the work that we've done on task and motion planning. And in this case, we find policies. And who is the uncontrollable agent? Typically a human. Okay, the human is the entity that you cannot really control, right? And we do want robots that work with humans. Okay, we want these robots out of the cages. We want them closer to humans. But you know, humans are unpredictable, all right? Humans may help. Humans may be malicious. Humans may be lazy, okay, and do nothing. And still you want your task done. So how do you deal with this case? Here, let me make sure that we all understand the difference between plans and policies. You know, plan is what I show on the left. You have a way to go from your initial to your goal. Policy is a very different thing, right? Okay, for policy, you want to know what to do under many different circumstances. And in this case, when you have an uncontrollable human, you want to go towards policies, right? You want to have a better understanding of what could possibly happen in your environment. So what is our goal here? We have some tasks to accomplish. We have some abstract model of actions that the robot can take and possible outcomes, and some abstract model of the human. And what do we want to output? We want actions to complete a task according to some criteria of optimality. We can do that with replanning. Yes, it has its advantages and disadvantages. A disadvantage could be runtime latency if you're not careful. We have contingency planning. Yes, you can do that, but you have to think about all these contingencies. And we wanted to investigate reactive synthesis, okay, for formal methods. It provides kind of a structured framework to reason about the things that can happen in your space. All right. So if you use reactive synthesis for the problem that I'm discussing, really what you're doing is the reactive synthesis is reduces to a game. So the players are the robot and the human. The game rules is the planning domain and abstraction that you need there, and I will get to that again. A winning condition is your task, and the strategy that guarantees that the robot wins is the strategy that guarantees task completion. Okay, so we have a huge theory to draw from, the theory from synthesis and reactive synthesis. Now, if we go with reactive synthesis, there are two things that we have to be careful about: the domain abstraction and the specification of the task. And we want a policy, as I said, that will guarantee task completion. Okay. Abstractions. Okay, abstractions. How do you abstract this space when you have a manipulator? Okay, you have a task and you have a manipulator. Yes, you can think about the nodes, let's say, of your abstraction graphs being the locations of your objects. And the edges will be of two kinds: the human actions and the robot actions. You have to make some assumptions. Okay, you cannot work with a general case. So the assumptions that we made is that the human cannot move an object out of the robot's workspace. The human can not hold an object indefinitely. The human has a bounded number of moves, because if you give it unbounded numbers, you can always undo what the robot does, and you'll never be done. And the robot is modeled in a standard PDDL pick and place domain here. Finding this abstraction automatically is a lot of work. Okay, and we have a paper that discusses how you can get to an abstraction like this for a manipulator. But assuming that we have this kind of abstraction, we have a nice logic that can give us, again, a finite automaton that tells us, how we can accomplish this particular task. Now I will jump, to what we can do, and by showing you this video. So the goal here is to build an arc. Okay, this arc has two black blocks as support, two white blocks as support, and a black block on the top. Okay, so this is the task, and you see that the robot here managed to accomplish the task. Now I'm going to show you this video again, and I want you to look at the human. Okay, see what the human is doing in this environment. All right, so here we go again. Oops, here we go again. Hopefully. I hope it's going to run. Okay, here the human helped. Okay, it put correctly placed the black box. But here the human hurts the task by taking a white block away. Nevertheless, the robot has a policy to be able to fix things, let's say, and accomplish the task. So this is what symbolic reactive synthesis gives us, and it's very interesting to play these games. Okay, but how do you get there? In order to do synthesis, you need to do symbolic synthesis. Otherwise, you have an explosion. Okay, huge explosion. It just doesn't work. Well, symbolic synthesis, fortunately, we found out, works very nicely for robotics domains. We have both our transition diagram and our DFA can be represented with Boolean variables, and the computations that we do really are Boolean functions as set, and we can represent the things nicely in the way that symbolic synthesis would expect things. I don't know if you've heard about BDDs, but BDDs compactly represent Boolean functions as sets. Here is an example. Actually, I got it from Wikipedia. This set, you can compact everything that is the same and reduce the space and the operations that you do on this particular structure. And for robotics, symbolic synthesis makes a lot of sense to me. And remember, I told you about representations at the beginning. I told you about abstractions, and we need to care about these things in our work. So let me give you an example to illustrate why symbolic synthesis and symbolic analysis makes sense for robotics. So here, the robot needs to grasp a cylinder. We don't care which cylinder, right? Just the cylinder. We can deal with all states explicitly, right? Well, that's fine, but if you have 1,000 of these states, what do you do? However, we can group equivalent states together. So in this case, the only state variable that we care about is that some cylinder is in the gripper. That's it. I mean, I don't care about the rest. So what I can do is that I can see all of these three options as equivalent. So this is the symbolic representation that I'm discussing. And we were successful, actually, in exploiting this idea. It was difficult at the beginning for us to switch our mindset, but we were able to represent our domain symbolically. Also, there is a whole theory about how to represent specifications, how to go from form of specifications to symbolic automata. So we used this work, and we represented. We worked very carefully with the abstractions of our planning domain. We had also LTLF specification. LTLF is LTL over finite traces. Finite traces because usually we're interested in construction tasks. We wanted something that is finite. We got again a symbolic representation using a tool called Mona. I mean, we didn't write that, but then we managed to work with symbolic representations and solve the game. And as a result, you have the videos that I showed to you before. Okay. So it forced us, this work on task and motion planning, to think about representations, to think about abstractions, to think about how to put together things, how to deal with discrete components, continuous components, and as you will see from the posters, how to insert different things like learning and different kinds of reasoning. All right, so I will finish now by telling you that once we got these results, of course, we were curious. What else can we do? How far can we push this? And we've moved from reactive synthesis now to probabilistic synthesis. So reactive synthesis was very nice, but still the model of the world is inaccurate. And we want to go closer and closer to world models that reflect the reality. And we want to keep and eventually improve scalability of our techniques. And scalability is a big thing if you're not careful with your representations. Before, I told you that our abstractions had here two kinds of edges, the human actions and the robot actions. Well, think about it in a different way. You can have the human here, and you can assign probabilities to the different actions that the human or the robot can do, right? So here, let's talk about the robot here. Here is a robot, I mean, maybe with a 0.7% or 70% chance to get to this state, 20% chance to get to another state. So in this way, you can model environmental disturbances and human disturbances. Why do we want to go to a model like this? Let me justify it to you. Well, you're working with a human, right? You may be working with an adversarial human. You may be working with a helpful human, right? You may be working with somebody who actually wants to help this robot get the task done, or the robot helping the human get the task done. This is illustrated a little bit in this slide. So here is the case where we have an adversarial human. And the robot could try to build, do whatever it needs to do away from the human, minimizing the chances that this human will interfere. But if we have a helpful human, then the robot may try to build things, build this arc that I'm working with in this example, close to the human, so that the human we increase the chances of the human actually helping finish this task. So this is stylized a little bit in this example, and I will be talking for the rest of my slides with building an arc with these three blocks. In order to get to probabilistic synthesis, again, you need a good abstraction. And here is my domain. Let me define my domain. Here is the arc I want to build. The numbers are the locations 2, 3, and 4. This is my gripper. Okay, the gray is the gripper. 0 is a location in the gripper. And location 1 is the else location, everything that is not shown. And when I want to describe a state, here is how I describe the state. The colors show where the two blocks are. So here is a transition diagram that formalizes what the robot can do. So for example, for this state, the robot may decide to pick the blue cylinder from the else region and stack it. And in that case, we're done. We can assign probabilities in this. Okay, so for example, here, there may be a chance that 90% chance that the robot will stack the cube and we are done, or a 10% chance that the robot does nothing, okay, and we remain in the same state. Okay, we can do the same thing for the human. Actually, in our work, we assume that this is given to us. But for example, this means that we have a human starting, let's say, in this state, maybe with 50%, let's say 15% chance it stacks the blue box and we are done. Taking all this together, you can get to something that we call the manipulation MDP that encodes all this information, plus other extra things that I didn't talk about, as whose turn it is and how often do you check for changes in the environment. And then you go again to solving this MDP. But in order to do that, you need to worry about your representations, you need to worry about your abstractions. We worked again with this idea of BDDs in order to be able to use tools that can actually deal with the complexity of the manipulation domain. Remember, it's not a mobile robot here, it's a manipulator, all right? It's a manipulator with high degrees of freedom. So we managed again to do the same kind of representation and also worry about variable ordering, because synthesis, can assign values to variables randomly, but we have a robotics domain. Okay, this is a CAN, and the CAN needs to be here on the table. So we worked with encodings. You can find this in our papers, and we found actually that there are encodings that make sense for robotics and can help us solve the problem that I discussed at the beginning. So here is an example with an adversarial human. The robot does not expect the human to help, so it builds an arc far away from the human. In the second case, the robot expects the human to help, so it doesn't do anything with this white block. It leaves it where it is and lets the human help it complete the task closer to the human. Okay, I'm done. Part 2 is completed. What I wanted to say, I'm going to go back now to my slide saying that we use the task emotion planning problem to talk about meaningful interaction of perception, state estimation, planning, and control. We use this domain to understand the role of symbolic reasoning, formal methods, and learning. We try to understand modularity. We try to understand abstractions. And Ken Elimelech, who is a postdoc in our group and who is somewhere here, yes, will be giving a talk about our initial effort to understand the task emotion planning skills. And I think, as I said before, that this can help us go to long horizon tasks and move towards autonomy. I will finish here by thanking the students who did this work, because I did not do this work, I'm just presenting it. A number of students have been involved in the topics that I discussed. A number of collaborators have been involved in the tasks that I have discussed, our funding agencies. And I will close by thanking all of you for your attention. Thank you very, very much. Okay, all right, we have some questions.
Curious, a lot of your past work was in motion planning.
Yes.
And you're talking about task and motion planning and all the instances you gave with the tabletop.
Yes.
So I guess the question is, where do you see a role for task and motion planning in early navigation tasks? And if so, would you use the same techniques exactly, or is should we be separating task and motion planning from manipulation?
No, I'm not separating them. I think we have a particular expertise in working with high-dimensional systems that other groups do not have. That's why we focused on this case. But no, I don't see them separately. Actually, I think there are unifying themes that will be used. It will be the same if you have a mobile robot, it will be the same if you have a manipulator. And there are people like, let me mention Hadas Kresgazit, who is working with reactive synthesis, for example, with mobile robots, and it's showing similar. She's getting to similar observations than the ones that we are getting to, and it's very, very interesting to see. So I think there are underlying principles that can be used uniformly. We chose to focus with manipulators because I think there are very, very few groups who understand how to do the motion planning in this kind of cases, and we understand also abstractions. And for these kinds of systems, I think to an extent that can help this problem. Absolutely.
An observation is that the balance between how long it takes to do the planning versus execute.
Yes.
Could be much longer, and so that can get you into
very interesting problems. Yes, very interesting problem. I didn't get into this at all, but you see, this is extremely important, right? If you have a budget for the timing, or if you want things to be done at certain points, then you have to insert a much more than I described in this talk. And I would be very happy to talk to you about this. Yes.
So maybe following on the thought, you start with full facial motion, so we have a manipulation, as you go to mobile robot integration. So if you look at novel way in, have you thought about vehicles that have more dexterity, like the systems we go with active systems, where we're able to move the body in full 6 space. So the navigation problem is actually like docking.
Yeah, we have not, but I think this is a very interesting case. Yes, we have not gone into that. Luis.
Yeah, so connection to molecular control, and that can allow you to predict and something-based approaches could be great for kind of hallucinating the future or predicting the future, and in connection to both task and motion planning, and perhaps even give feedback. I know it's a big problem, the dual sided communications, where the execution layer can give sort of a prediction score to either the task or the motion planner. So I wonder if that's areas that you're investigating for having sort of robustness and real-timeness of these.
So we want to get there. We are still not there. We want to get there, and I think you have a very good point there, Luis. Okay, but I cannot tell you that we have work going on in this domain right now. But I think the connection with model predictive control is going to be critical, for deploying these things in the real world.
Thanks.
Thank you.
Right. Thank you, Lydia, for this wonderful talk and setting up lots of discussions. We hope to continue these discussions.
I would love to, and this is why I structured the talk in this way. I hope to generate some discussion, and I would love to, and my students are here, and we would love to hear your comments.
So let's thank Lydia again.
Thank you.
And I'll hand it over to UK to introduce the next speaker.
All right, our next speaker is Ken Fleischman. Ken, you can come here and set up your laptop. All right, so let me introduce Ken. So Ken Fleischman, he's a professor of School of Information here at UT Austin, and he's a founding chair of the executive team of the Good Systems. And so it's a big effort here at UT, and that's what he's going to talk about today. He's also a founding director of the undergraduate studies for the iSchool's bachelor degree for informatics. His research and teaching focus on the ethics of AI and more broadly, the human value, the roles of human values in the designs of the information technology. So Ken has won many Best Paper awards, probably too many for me to cover. And one fun fact I'm just gonna say is that Ken actually did his undergrad in double major in computer science and anthropology, and then he went to do a PhD, master and PhD study in science and technology studies. Why that caught my attention is because my wife is an anthropologist, so I know what kind of interesting conversation can happen between robotics research and anthropologists. And Ken is the one who speaks both languages, right? So I think his talk is guaranteed to be interesting. And so without further ado, Ken, the floor is yours.
Thank you so much, Yuki. Really appreciate it. Thanks, everybody. Okay, so today I'm going to talk about Good Systems UT Grand Challenge. This is one of 3 campus-wide research grand challenges that we have here at the University of Texas at Austin. These are 8-year moonshot initiatives to explore new areas in ways that are societally relevant. And that's where the computer science anthropology combination comes in, understanding both the human and the technology and trying to put them together. We have an incredibly diverse team. Actually, one thing that's really different about Good Systems relative to many other Grand Challenge initiatives at other universities is our initiative was really done, the Bridging Barriers Research Grand Challenges were done from the bottom up. So it's usually at most universities, the president, the provost, the VPR sit in a smoke-filled room and decide sustainability and cancer, that's what we're going to focus on, whatever they think the hot topics are. Here, the administration actually trusted the faculty and enlisted the faculty's assistance in coming up with white papers that would propose grand challenges for the campus and then connected us. So it's actually Peter's white paper on, there were many white papers that went into good systems, but I would say that Peter's white paper on ethics of AI was the one that's at the heart of good systems that led to bringing together people who wouldn't otherwise have met each other. That was how Peter and I met. It was how many of us on the executive team met. And it was really an honor to get to be the founding chair of Good Systems and lead us through that process of getting approved and launching. So we launched on the fall of 2019. So we're in our third year right now. As the president described, we are working to ensure that the needs and values of society drive the design of AI technology. So we focus on ethics of AI and ethics of robotics. So that's the focus of Good Systems UT Grand Challenge. And so this slide describes we're bridging barriers between disciplines. Of course, at many universities, including at your universities, it can be challenging to interact just between electrical and computer engineering and computer science, let alone anthropology and computer science, or the School of Information, where I'm a faculty member, and computer science or other units across campus. So here we have, I'll have a slide later about the range of different units that are participating, but it's over 35 different units across campus participating actively in Good Systems. And these are, again, moonshot initiatives with big goals. And of course, AI and robotics are touching just about every part of our lives and are poised to do only more in that regard. And it's really important that we're using them as a force for good in society. We're using them as a force for equity, a force for justice, to make the world a better place. So again, AI is in all of our lives. There are all these unintended consequences. So this is part of the challenge. Of course, we like to work fast, break things, see what happens. So actually the quote from Ian Malcolm in Crichton's Jurassic Park I find inspirational. Your scientists were so preoccupied with what they could do, they didn't stop to think what they should do. So this thought process, this decision of like, what might happen, how might it occur? It's hard to predict in all cases what are the possible consequences of technology, but it's important to be thoughtful about that and not just, that's someone else's problem. We really can't afford that. Of course, in medicine and in law, we have licensing that can be revoked. So you can lose your license to practice law or medicine because those are life or death professions. Because you might be on either side of a capital murder case, you might be saving a patient in an emergency heart surgery. Technologists are increasingly also doing things that are life and death situations. If you're designing a Boeing 737 MAX 8, that's a life or death situation. If you're managing a robot that, one wrong move might kill 8 assembly line workers, that's a life and death situation. We don't have that same recognition and that same licensing for roboticists and other technologists, but we have that same responsibility. It's really important that we're considering that seriously. At the same time, the lawyers and policymakers, if you've seen some of the hearings on Capitol Hill, still talking about vacuum tubes and having no understanding of the business model of the social networking companies, you can really see that we have a big gap between technologists need to think more about the societal implications, and the lawyers, policymakers, other folks on the societal side need to better understand the technology and what might happen. We need to bring those expertise together. That's what Good Systems does. So the Good Systems framework is about defining, evaluating, and building. So we define what it means to have a good human-AI partnership. And so part of that is defining good, but also part of that is defining the system. And the system is not just the technology. The system is a socio-technical system. So it includes the humans and the technology working together in a partnership. We want to evaluate the goodness of systems, existing systems, that we can improve upon them, as well as once we built our systems, evaluate their goodness so that we can assess the degree to which they're really meeting our goals and criteria. And finally, how we can build human AI partnerships that benefit society. So at the end of the day, we want to build something, we want to put it out there, but with an understanding of what's going to happen and with careful evaluation of making sure it's achieving what we want it to achieve. So again, AI technologies are helping us solve complex problems in nearly every discipline and industry. So our grand challenge is to design AI technologies that benefit society. So these are the collaborating units. Again, over 35 different departments. Actually, that was an old count from before. We have just announced our summer faculty fellows, summer graduate fellows, and we're hiring some undergraduate research assistants for each of our 6 core research projects as well. So we're significantly expanding the scope of Good Systems, which is already pretty broadly across the campus, you can see. So you can see, again, I'm a professor in the School of Information, so you can see the iSchool. You can see computer science, of course. You can see many different departments in the Cockrell School of Engineering. You can see the LBJ School of Public Affairs. You can see TAC. You can see the UT libraries. Pretty much spans the spectrum of the campus. You can see College of Liberal Arts, English, for example, there. So these are some of the units, architecture, some of the units that our executive team are from, also the Moody College of Communication. So really, again, spanning the spectrum of the campus. So we launched in the fall of 2019. We started out with 10 one-year projects. We organized a conference on informatics education in March 2020 with funding from the Public Interest Technology University Network, which focuses on making sure that technologists not only go into jobs in industry, but also that we have good technologists in government and nonprofits, so we don't have situations like healthcare.gov that crashes, and for the first several years everyone hates a new law simply because they couldn't build a good website. So then we have actually in our second year we focused on collaborations with the city of Austin. So we played a role in the contributing to the development of a master interlocal agreement between UT Austin, the city of Austin, which is a 5-year partnership between UT and the city. And in our second year of the 11 projects that we launched, 7 of them were direct collaborations with the city of Austin. And several of our core projects that I'll talk about in a moment are also in collaboration with the city of Austin. And we partnered with World Economic Forum last spring, and then we launched our 6 core projects. So I'll talk about those 6 core projects a bit. I just wanted to give an overview. There's a lot of work going on, a lot of brilliant people involved in Good Systems, but I wanted to give you a taste of some of the work that's going on across all 6 of the core research projects. So before I get to that though, these are some of the first-year projects that we've done. So the AI Austin housing analysis, looking at housing affordability, urban health risk mapping. Another important issue is seeing where, of course, there are huge disparities in terms of the health impacts of pollution, for example, environmental justice issues, optimizing EMS response, so actually improving the time for EMS response. Again, life and death, that 88 seconds could be someone's life that you've just saved potentially. And then another project, AI equity and homelessness. This project was really funded by Good Systems. It's now funded by the city of Austin in partnership with the Downtown Austin Community Court, and was recognized as the Metro Lab Innovation of the Month for July 2020. So a lot of exciting projects, but we did 2 years of 1-year projects, and that gave us a taste of kind of what are the important areas in ethical AI and ethical robotics, but we wanted to do deeper investments. We didn't want to spend 8 years just doing 1-year projects. So after 2 years, we formed 6 core research projects that form the remaining 6 years of our 8-year mission. So those 6 core research projects are AI and racial justice, being watched, curbing disinformation, smart cities, living and working with robots, and smart hand tools. So I'll talk about each of those projects in turn. So AI and the future of racial justice focuses on achieving racially equitable AI, focusing on important applications such as public safety, transportation, and health. And in partnership with the city of Austin, for example, with health-based organizations and community stakeholders, again, defining, evaluating, and building what it means to build racially just AI technologies. And so the leads for this project are Craig Watkins from the School of Journalism and Media here at UT, Chandra Bhatt from Civil Architectural and Environmental Engineering, and Min Kyung Lee from the School of Information. Another project, Being Watched, embedding ethics in public cameras. So here the focus, of course, we have cameras everywhere. They can be very useful, but they're also, can raise some interesting privacy issues and concerns. So how can we enhance access and usability and improve social acceptance of these cameras and video data while handling issues like privacy? So how do we mitigate privacy risks and manage those risks? Actually, we had a great talk by Ed Cottrell from Microsoft Research a few weeks back in our Good Systems Symposium. One of the points that Ed Cottrell made in his talk was, we often think of these as trade-offs. So on the one hand, there's like so much information we can get, and in terms of safety, for example, that we get out of having a camera, but we also have this risk in terms of privacy. We often think of how do you balance that trade-off between safety and privacy. But in some cases, let's think about, are there ways that we can optimize and design for both? So can we design technologies, design systems that both safeguard privacy and promote safety, and do those together and try to advance both? So in many cases, we're trying to take these values and not just thinking of them as pure trade-offs, but how can we optimize for both? And so the leads on that are Sharon Strover from the Moody College of Communication, Maria Esteva from TAC, and Atlas Wang from Electrical and Computer Engineering. Another project is on the important issue of disinformation. So of course, disinformation is part of our everyday lives. It's been a huge issue in terms of how it's so easily spread via social media. And so here, the researchers are applying explainable AI to study disinformation, because one of the challenges with disinformation is getting people to trust any kind of labels, whether they're human or machine generated. Who is generating that? What's it based on? Why should I trust it? Why should I believe it? So if you use explainable AI, at least you can show some of the underlying data. At least you can try to provide a basis for that and not just trust me, I know better than you. So that doesn't work very well for most people. And also working to ensure fairness and bias mitigation in the NLP work that they're doing. So that's co-led by Matt Leese in the School of Information and Diraj Murthy from School of Journalism and Media. Good system for smart cities. So in this project, their goal is, as it says, build a digital twin of the city of Austin, and to basically take all the data that's out there. And so many, Austin does have an open data portal. It's got a whole bunch of data there, but it can be challenging to actually navigate that data and make good use of that data. Other organizations, entities, agencies have data as well. That data isn't necessarily interoperable. So trying to make that data interoperable, trying to identify data bias. There are a lot of limitations with data. Actually, Meg Maratha has done some really important work. A student at University of Michigan School of Information has done some really important work on how data for epilepsy and how physicians diagnose epilepsy and how they're defining a seizure. And if I understand Meg's work correctly, basically you would think of that as being an objective measure that would be based on how many of seizures per period of time. But in fact, Meg was able to identify cases where physicians were interpreting what did and didn't count as an episode based on what diagnosis it might lead to, which aligned with what they thought was best for the patient. So another case actually from our own work on the AI equity and homelessness study was one of the questions. There's this instrument called the VI SPDAT. The VI stands for Vulnerability Index. Basically, it's used as an assessment tool to figure out how, for triage, how much need someone has for care. Basically, how likely is someone to die if they're in their current situation without any kind of services provided, to prioritize services. And so one of the questions on the instrument is, do you have access to food? And one of the participants said, yes, I do. And the caseworker who was administering this actually knew this person and understood their life and had seen them getting access to food. And they said, oh, do you mean when you get food from the dumpster? And they said, yes, that's what I mean. And then the answer is no, they don't have a steady, secure access to food. But based on the instrument, based on how the participant understandably interpreted the question, they were going to answer in a way that would get them less care. well, they needed care. So the data that we have is often very unreliable and very problematic, even unintentionally. That's an unintentional case where someone is accidentally disadvantaging themselves just based on how, maybe the question could have been written more clearly based on their interpretation. So the co-leads for that are Zhenfeng Zhao in the School of Architecture, Nok Tran in math, and Wei Jiaxu in tech. Okay, big one here, living and working with robots. And actually, we've got many of the co-leads of this project here in the room. So, sorry I hope I don't butcher this too much. Apologies if I do. But as I understand what Peter and Joydeep and Luis and others are doing is designing autonomous service robots to interact with people on UT Austin campus. So they're designing robots to uphold human values, not cause unintentional harm, improve campus quality of life. And so to see robots as a good addition to the campus, actually working and interacting in real environments. So I know one of the partnerships you have is with UT Libraries to deploy them at the UT Libraries in a meaningful case. And another is actually with Houston-Tillotson University, because once you've tried UT Austin, it's important to try in other settings. And Houston-Tillotson is the oldest university here in the city of Austin, also HBCU, and is a partner on that project as well. So it's really exciting to see sort of citywide deployment, starting here at UT, then the HT, and then across the entire city. So it's a very ambitious, very exciting project. And too many co-leads to list, I guess. Okay, Sam Baker, English, Joydeep Biswas, Computer Science, Aaron Choate, UT Libraries, Justin Hart, Computer Science, Elliot Hauser, School of Information, Katie Pierce-Meyer, UT Libraries, Louis Sentis, Aerospace Engineering, Samantha Shorey, Communication Studies, Carrie Stevens, Communication Studies, Peter Stone, CS. Okay, and then the last of these, sorry, I know this is quite a whirlwind tour, but the last of these is making smart tools work for everyone. This is a core research project that I'm co-leading with Raul Longoria in the Walker Department of Mechanical Engineering and Sherry Greenberg from the LBJ School of Public Affairs. So we're designing smart hand tool systems that empower workers. So we're looking at applications like manufacturing, construction, maintenance, repair. Of course, there are increasingly robotic solutions being created in those contexts. And increasingly, this is threatening blue-collar jobs in many cases. We're looking at, can you take the tools that workers are using that probably haven't changed much beyond ergonomics for many years, and can we give them some sensing capabilities? Can we leverage IoT and edge intelligence to actually give workers feedback to help them learn faster, learn better, avoid repetitive stress injuries, avoid workplace accidents? Can we broaden the middle school workforce? So there's really a gap. One of the applications, one of the occupations we're looking at is welding. There's a huge gap in welding in terms of the many jobs that are available and the relatively lower number of skilled welders that are here in the workforce here in Austin, Texas, and also nationwide. So a lot of middle school jobs, there is a gap, there's a need for more skilled workers. So being able to expand and broaden the workforce in terms of education, in terms of ability, would be a way to address this middle skill gap and to keep some blue collar jobs. So that's the purpose of the Smart Hand Tools project. So these would of course be networked together, and there would also be a digital twin. And this way we're going to be modeling the use of the tool and observing how the worker is using the tool and optimizing for the worker's use of the tool. And so we're starting, this was our sort of toy project. Again, we're using welding as our main application now, but we're using a small rotary power tool. As you'll see in one of the next slides, we have quite a team of people with very different backgrounds, so we wanted to make it pretty safe. But also it has, we use 4 different bits. So you can then have 4 different activities and you can try to sense the activity. So eventually what we're trying to do is to be able to, help novices learn from experts. So to be able to detect the skills that experts have and help novices to acquire those skills. But the most fundamental thing, before you can run, you have to walk. The most fundamental thing is to figure out what activity people are performing with the Smart Hand tool. So we did testing with these 4 different bits in order to figure out. And so we had a lot of engineers, but also we have a sociologist and a lawyer on our team. So we had actually one person not pictured here, so 7 different testers of the technology that we were assessing this with. And for the sensor data, we had all these sensors, so acceleration, body rotational velocity, magnetometer, and also the current and the sound. And so based on this, we were able to model, and so here's the confusion matrix that we got for these 4 different activities. And this was a very early pilot. So in the first year of a 6-year project, and this is work that we did in the fall, but we're able to, very well predict the which activity is being performed. The next thing is which worker is performing it, then differentiating skill in terms of highly skilled workers versus less skilled workers, and then identifying gaps, identifying lacks of skill in the less skilled workers that you can give feedback in order to help them to perform as well as the high skilled workers. So that's the trajectory of that project where we're at right now. Again, Sherry Greenberg from LBJ School of Public Affairs and Raul Longoria from the Walker Department of Mechanical Engineering are our main collaborators in this project, but it's also a broad team across many different units on the campus, as is the case for all of Good Systems. So just really fabulous folks to get to work with. Coming soon, we do have some things going on here on this campus. One is we have a portfolio program in ethical AI that actually Luis and Peter and a bunch of us are working on. And so I guess Joydeep will have this pretty soon. I think, so Zhenfeng Zhao, who's the lead, just submitted the paperwork earlier this week. So we're waiting to hear how this is going to turn out. But a portfolio program here at UT Austin, it's sort of like an interdisciplinary minor for graduate students, either master's or PhD students. So it's a collaboration between the Department of Computer Science, the Department of Aerospace Engineering and Engineering Mechanics, the School of Architecture, and the School of Information. So that'll be a great opportunity for our students and a great chance for that kind of interdisciplinary interaction. Students take classes from 3 different departments in that portfolio program. And Luis has a really awesome robotics course. Joydeep does as well. Peter's going to be teaching a really awesome course as well, along with Tina Peterson. So that's going to be a really exciting course and introduction to ethics for AI and robotics. And then last thing is that there's a new journal that's going to be launching, the ACM Journal on Responsible Computing, which is going to be carrying forward the focus on ethical AI and basically Good Systems approach to focusing on what is it that technologists should be thinking about as we design and deploy new technologies. So I'll be the editor-in-chief of this new journal, and we're going to have the website launched this summer. We're planning to publish our first issue next year, our first volume. So please stay tuned and definitely keep us in mind as a potential venue for your research down the road. And Peter is serving on the advisory board for the journal. Awesome. So thank you all very much. Any questions?
Thank you, Ken, for this overview. I think this Good Systems work is fantastic. I'm really happy to see the support and the enthusiasm from the community around this. In thinking about it, I think it's very important, as you've highlighted, to teach the practitioners to think about these things and put them at the forefront of their mind when planning experiments, when planning ML systems, deployment, operations, et cetera. The other side of it is, as you highlighted, the lag that exists in policy. And I was curious, not so much from your own work, because I know that you're very much a researcher, but is there any sort of tie-in to the LBJ school and essentially lobbying, right? That's how you make policymakers care about the things that you care about, is through lobbying efforts. That's how you educate them. That's how you raise awareness and bring forward the great research that's coming out of Good Systems. Is there a policy influence side via lobbying that exists via Good Systems, or is that an entirely separate activity?
It is absolutely part of, that's a great question. Thank you so much for that great question. It's absolutely a key focus for Good Systems. We were fortunate to add 2 members to our executive team recently. Luis Sentis is one of them. The other is Sherry Greenberg from the LBJ School of Public Affairs. Sherry was in the Texas House for 10 years and also served as a special advisor to Mayor Adler. So she's one of the most connected people in the city and in the state, and also a great scholar in public affairs and public policy. So one of the first projects, actually around the time that Good Systems was being launched, we had funding from Cisco Research to look at that gap that exists. And so we interviewed AI researchers. We also interviewed folks in policy and in law, and identified some of those aspects of the gap. And part of what we're trying to do is to train interdisciplinary folks on both sides. So not just to get the technologists to be aware of the societal implications, but yes, also thinking about in terms of public policy and law, how to get folks more trained and educated and proactive. That is, we in our informatics major that I'm the executive, that I'm the director of, we have a required ethics course as part of that. And we're creating this, group of very socio-technically expert folks going in. One of the outputs of the work that Sherry and I did was to do a white paper for the Day One project, which focuses on, they come up with proposals that would be things that a new administration could come in and start to launch. And so we propose to increasingly centralize AI, sort of centralize, but also connect AI research and AI policy to make sure that the research was driving the policy and that the policy was informed by the research. We have seen some progress in that regard in recent years in terms of trying to connect those. So it seems like there's some progress. There's still a lot to do, but yeah, Sherry Greenberg is really our sort of local expert on the team. And since she's co-leading the Smart Hand Tools project with me and Raul, that's been a great opportunity to think not only about the technology, but also the impact it's going to have on society. And of course, jobs and job loss, job creation, and manufacturing in this country right now. We've seen the issues with supply chain during COVID. Of course, some countries are still having lockdowns, and as well as we have, of course, some very unfortunate situations going on in the world right now. So that's all disrupting our supply chain. It's really important that we're thinking about how we can, make sure that we're still manufacturing here in the US, and we think our work would help to achieve that. Great question, thank you.
Anyone else? Over there.
Understanding the domain in very domain-rich areas. How are you training the students to do the research? Not the ethics and the policy, all very important, but the actual domain analysis and working with it. How are you structuring that?
That's a great question. So, and our this portfolio program in ethical AI is a part of that. So there are domain courses in robotics, for example. I know that like the work that Joydeep, that you do in robotics, and that Luis and Peter do in robotics, that you're actually collaborating with the domain experts. So there are 2 members of the UT libraries on the team. So in that sense, when they're actually thinking about deploying in the UT libraries, they have folks with that expertise. And also across that team, we've got aerospace and engineering, CS, lots of different disciplinary expertise. I think what happens in a project like this is the students that we're training are inherently learning interdisciplinarily from the get-go. So any student that Peter has now is not like purely a CS student. They're going to have that hybrid expertise. Peter, go ahead.
AI and robotics, but it's not just robotics, but the domain that they're thinking of focusing on, first time it's been talked with still in development, but is there's COVID response, pandemic response. We've developed a simulator collaborating with epidemiologists here on building a sort of agent-based model of pandemics that we can then have students come in and think about what kind of interventions could be made from an AI perspective, and what will be the ethical implications, societal implications. So very much in the context of a domain that's been built up with these consultations.
Yeah, thinking, and that's so interesting. And this whole idea of the simulation and modeling with the digital twins, thinking about the ones like the smart tools and the EMS. Are you using a Delphi cognitive work analysis? Are you training your students in those formal methods, or is it more we're building the system and then letting everybody explore together?
Yeah, I can speak best to the Smart Hand Tools project since I'm co-leading that initiative. So for that project, we're doing participatory design and value-sensitive design throughout the design process. So we're actually going to be our next two. Okay, so I should have mentioned that as we were doing the Smart Hand Tool in the lab, the rotary power tool, we were also interviewing students from Longhorn Racing. So Longhorn Racing is a group here on campus that builds combustion, electric, and solar vehicles. And so we're interviewing students about their tool use. They were the ones that highlighted for us how welding was the really challenging application for what they were doing. So we just put in a proposal based on the application of Smart Hand Tools to welding and building smart welding tools that came from interacting with our student participants. Of course, those are UT students, so we really want to go out in the field. So we're now exploring interviewing blue-collar workers, and specifically blue-collar workers who will need accommodations in their work, and trying to understand what accommodations they would need and how Smart Hand Tools could adapt for that, as well as the training process and how folks learn to weld and how we could maybe improve and speed up that training process. So those are some, and we're collaborating with and gathering data from participants using work from more of a qualitative social science perspective primarily. I hope that helps. Thank you.
Okay, folks, for the interest of time, so we're going to end this keynote session because there's going to be a class in this room in 5 minutes. So if I may kindly ask you to step up because we have a coffee hour. So you're going to continue the discussion over coffee, and we'll come back in 11:15 in this room. So for the spotlight talks. All right, see you soon.
Thank you. Thank you.
Appreciated the Obamacare reference.
But that actually
assessment tool. Like if you want to know
that you?
There's a company. Right. Yeah. Okay.
Make sure that's using the right audio. Oh, it's not. Yes. Hello, everyone. Welcome back. Sorry for there's some Wi-Fi issues going on right now. So yeah, I hope you all enjoy the poster sessions and the coffee breaks. Now we're going to have very five nice spotlight speakers. So first, let's welcome Professor David Friedovich Kale, who is from UT Austin. Yeah, please take away.
All right. Thanks, everybody. Really happy to be here. Well, I guess I'm always here, but anyway, happy to be here and talk with you all about what's going on in my group. So I started here back in August. Our group tends to focus on control theory as applied to lots of different multi-agent problems. So generally multi-agent problems. So what I'll tell you about today is recent work we've been doing in kind of efficient solutions for non-cooperative games that describe those types of problems, and also some connections to efficient learning techniques in those games. All right. Great. So when I talk about, there we go. Yay. When I talk about non-cooperative situations, multi-agent situations, there's lots of different things that I want to have in mind. So the most natural one for me to think about, so I'll suggest that you all try to think about it as well, as traffic. So when you're thinking about driving in traffic, you're thinking about wanting to accomplish a particular objective. Typically, I want to make a right turn in 2 blocks, or I want to make sure I slow down for the stoplight, whatever it may be. But every other car on the road probably has a similar idea of what they want, and those objectives can be in conflict over time. So game theory is the language for mathematically describing these types of situations. Lots of other application areas that I'm not really going to dwell too much on in this talk, but for whatever floats your boat, if you like power systems, that's a good application area. If you like transportation grids, that's another good application area. So what we'll talk through today are just the mathematical basics of what games are, and specifically dynamic games that are played over time. So I want to make sure everyone's got a sort of similar footing. Talk through some modern solution techniques for these games, and then I'll give a little vignette towards the last few minutes of how to talk about learning meaningfully in these types of situations. So if you've seen games before, probably you saw static games. At least that's the first setting that most of us learn about. So Prisoner's Dilemma, Tic-Tac-Toe, not Tic-Tac-Toe, Prisoner's Dilemma, Rock, Paper, Scissors, games like this. You play once, you make a decision of what your action will be. Everybody does the same thing, and you see what happens. Every player can have a different idea of what happens, So I've kind of written that down as this function j. The vector u is the kind of concatenation of everybody's actions. So whenever you talk about a game, there's different types of solutions or kind of important points in the strategy space that we might care about. Throughout this talk, we'll use the simplest one, which is a Nash point, Nash equilibrium point, and that's kind of akin to an optimum point in an optimization problem. So where everybody is unilaterally very happy with their solution, fixing everybody else's actions. But in robotics and control theory, we tend to care about systems that evolve over time. So time plays a really key role, and in game theory, the way to express this is in the language of a dynamic game. So here, I've kind of rewritten the objectives of every player to depend upon the state of the game X that's evolving in time, actions that players take over time, so I've subscripted with time. So we'll use this notation throughout, and we can still talk meaningfully about equilibrium concepts like Nash in this type of setting. But once we talk about dynamics and time, we need to start introducing a few other subtleties. So we need to introduce things like rules. Okay, if you play chess, there's clear rules to the game. If you're talking about the physics of cars on the road, there's clear rules that govern how cars can move. If they accelerate a certain amount at some time, they can't be going faster than a certain amount at a later time. So rules, dynamics govern the evolution of state over time. And a very subtle piece, at least to me, is what information is available to each player at each time. And if you kind of make different assumptions about what players get to see when they make decisions, this really changes the character of an equilibrium. So there's some really, real subtlety in defining these things. But once we've defined a game, so for example, to model traffic, we're left with the question of how do we solve it. And so some work that our group has been doing over the last, so when I was a PhD student and continuing here, we've been doing the last few years, has been coming up with efficient techniques to solve these games. The character of these solutions, we tend to think about them, a game as a set of coupled optimization problems, where what we do is think about what the optimality criteria are for every player simultaneously. So if you do that, you sort of start writing down KKT conditions and just follow your nose for a while, and you're left with a root finding problem. And so modern solution techniques that we and others have developed essentially boil down to finding efficient ways to find roots of first-order conditions that are coupled between all of the players. So if you do this, you basically can boil the problem down to something that looks a little bit like Newton's method if you're familiar with root finding techniques. And the kind of cool thing here is that we can show that each step in these iterative algorithms boils down to a very efficient recursive computation that, for folks who have seen kind of linear quadratic regulation, things like this, looks a lot like that. So if you mix in a few details from optimization, you're left with kind of an algorithm that is iterative and looks like the diagram I've shown on the right, which boils down to repeatedly solving games which are simpler and have closed form solutions. So we've shown that these are efficient real-time algorithms, tested them at scale on Boeing test aircraft, for example, and so this is pretty much the state of the art in solving mathematical games of this variety. So what I want to talk about is now that we have these techniques for solving games in real time, this opens up a huge world of other opportunities for us to study the interactions of non-cooperative agents in real life. So what I want, that's kind of going to be a focus the next couple minutes. One thing that I've judiciously ignored so far, that's going to be the kind of basis for the next part of the talk, is that Nash equilibria don't always exist. This is something extremely well known in the literature. You just got to look at rock, paper, scissors to see this. So if you think about rock, paper, scissors, think about if you played, rock, let's say, what would your opponent like to play? You'd probably play scissors. So you can kind of start to go around in a circle, and this is not going to have a pure Nash equilibrium. But what's very well known is that mixed Nash do exist. So you can see this kind of non-existence of pure Nash, existence of mixed Nash. I'll explain what I mean by that in real examples too. So you can see that, for example, in a pursuit evasion game. So something like playing tag or capture the flag, something like this. Classic examples in game theory. And so here what I'm showing is on the right, like a pursuit evasion game where red wants to catch blue. And I'm showing just one candidate solution point where they've each chosen to follow some trajectory over the next couple of seconds. And what's happening is, this is probably not in equilibrium because the blue player would like to not get caught, so they're not happy. So this is not an optimal equilibrium. So the point is these non-existence issues do naturally appear in real interesting ways, continuous dynamics, etc. Nash, I said, can exist if we make a slight modification to what we mean by strategy. And this is what people mean when they say mixed Nash. So when you talk about a mixed Nash, say in rock, paper, scissors, you're talking about randomizing your choice between rock, paper, and scissors. So you're choosing a distribution. You're choosing to play from a probability distribution. And you can see the same thing happen in that pursuit evasion game that I was illustrating before. If each player has, say, 2 trajectories that they can choose randomly between, there does exist a Nash equilibrium in that more complicated space. So what we've been able to do is essentially characterize equilibria in games that are kind of lifting the strategy space to include both pure and mixed Nash equilibria, and learn to solve pursuit evasion games in those sorts of games. So I'm essentially waving hands vigorously at the math, so I'm assuming that people are reading very quickly in this limited time here. But basically, what's boiling down is that we're allowing players to choose trajectories, choose multiple discrete options. Think of these like motion primitives or something like that. But also choose with what probability will they follow each option and solve a game in this limited context. And this actually, we've shown that this dramatically outperforms other notions of equilibrium. So there's some mathematical subtlety here of how we actually solve these games, but for the sake of time, we'll neglect this. And the TLDR is that we can characterize the equilibria and show that the equilibrium points are different than those that existed before. We can show that they can represent stronger policies, stronger solutions than were available before. We can show that we can learn to play in these strategy spaces efficiently. It's an iterative algorithm that takes milliseconds per iteration, so quite fast. And we can show that these policies outperform existing notions of strategy spaces. So the take-home message is pure Nash don't always exist, but with these computational tools we've been developing, we can solve in more complicated spaces quite efficiently. So that's all I got. I'd love to take any questions just after the session.
Yeah. Cool. Thank you. Thank you, David. Yeah. So next we're going to have Professor Robert Ambrose from Texas A&M.
Hi, I'm Rob Ambrose. Thank you for inviting us to this. I'm hopeful that this will be maybe the first of others, and I would like maybe to get together some of the other sites, figure out, maybe plan out the next 2 or 3 of these to build some momentum. And I also appreciate what we're seeing here at UT, where we've got faculty from different departments and even different schools within the same university working together, and that might be a good example for the larger region. So thank you. I'm working on some new initiatives at Texas A&M, having retired from NASA, and I'm hopeful that these will be new initiatives that will help the region, and I'd like to engage you on some of those thoughts. But at the same time, I want to have a fun project on the side. So if you look back at what I did at NASA, where I led the robotics program, there are a number of robots that I didn't get to build yet, and I still would like to go after. And so I'm going to have some fun projects on the side, and I want to tell you about one of them here. So we built, let's see how this plays. So we built a robot in 2003 that was very unusual. And there was just some things about it that caught my eye, and I decided that I really wanted to come back to it. That's kind of unusual. I mean, how does that work? Is there like a robot schnauzer in there running around? Kind of unusual, a little choppy with the video, sorry. I think this was shot on VHS. You see my student, Lyndon Bridgewater, he was a senior at U of H. You might see me back when I had a red beard walk by. How does that thing work? Is there a gyroscope? That's probably better than the schnauzer. How else might that work? And look how it's soft. It's compliant. In this case, it might have been a little too soft. You see some patches on the ball. Very low ground pressure, less than maybe 0.2 psi. So this could drive on very soft fluid even soils. You see it has a lot of weird dynamics and bouncing. And in hindsight, my student's trying to drive it open loop, and it's just, you can't do that. So what I needed to do, and I knew I needed to do it, was to give him an IMU. And I had an IMU. We just built a set of jetpacks for the astronauts, and I had a spare, and it was only $400,000. And I had one spare, and it was a 16-month lead item. And I just couldn't give these students my spare IMU. So I said to myself, you know, it's never going to meet its potential without an IMU. It'd be kind of like trying to fly a drone without an IMU. I mean, it's just, that's the way they used to fly model helicopters. It took a lot of skill, actually. So it needed an IMU, and the technology was just not there yet. But I had a feeling that there were some important things about this machine, and I would like to come back to it. Someday, I just had a feeling that the component technology would come down in price, and that I would be able to come back to this. So I kind of stuck a pin in this one, said, like, I'm going to come back to this someday, and this summer is going to be that day. So Lyndon, great young man, he's now the deputy project manager for the Viper rover that's going to the moon in 2023. That's kind of how he got started in robotics. I'm very proud of him. All right, let's see. That's how it actually works, and I'm not going to give it away. Well, you want to see it? It's actually a pipe with a 2 degree of freedom pendulum. And 1 degree of freedom, it can go continuously forever. That's the driving direction. And the other one leans left and right. So it's really simple. It's only 2 motors. Very simple. So I'd given him some design requirements, and I was stuck on the number 20, apparently. So I said it needs to be able to go 20 kilometers an hour, which for a 20 kilogram robot is really fast. In terms of like specific speed, that's unusual. And then I said it needed to have a 20 kilometer range, which energetically is enormous. And then I said I'd like it to go over a 20 centimeter step, which is like an 8-inch curb, and drive up a 20 degree slope. And for the first ball prototype, it didn't meet most of those objectives. It definitely was fast, and it was underweight, so check. I'm pretty sure it could drive 20 kilometers in range. It was just so out of control, we couldn't drive it to be able to test that. But I'm pretty sure it did it. It could have done it. But clearly it had some major deficiencies, and it absolutely did not meet the step and slope performance for a number of reasons in the kind of the parametric design of it. So the real deficiencies were this unstable driving. It needed a closed loop gyro IMU kind of controller for both driving and steering. And then the ball popped really easily. You know, that ball was aisle 4 at Toys R Us. And it was too low a pressure. We needed a higher pressure. And very hard to assemble. It was kind of a ship in a bottle kind of a problem. So there were some challenges there. But the superlatives, wow, it was so fast and light. And at ultra low ground pressure, that's very unusual to be able to operate at such low pressure. And I was thinking the moon, which has soft soils. When it inflates, it does a 4-to-1 volume change, which is really important NASA. So you could ship it small, and then it jiffy pops into a big robot. And boy, it can take a beating unless you pop it. But blunt trauma, it handles it. It's a ball. So applications, it's got, that pipe is a tubular payload bay. And NASA, we have a lot of tubular payloads. Working on soft soils, and I've never worked with a robot that would tolerate dust and thermal as well as this. It's basically a thermos. So it could really handle an extreme environment. It has no real openings to get stuff in it. So there's, hundreds of years of people building balls. And I mean motorized balls. There are lots of different kind of kinematic taxonomies of how to make a ball move. And some of them are really silly, but others are pretty good. And we're one of those. And then there's some really interesting research questions here. And when you have a new kind of morphology of a machine, it tends to open things up. And being able to control the pressure and adjust the dynamics of the bouncing is really exciting. So we're definitely doing that. But look at that second one. Turns out there is no aerodynamic data for a sphere rolling in a non-slip condition on a plane. There's a sphere in free air. There's a sphere spinning in free air. But with a non-slip condition up against a planar surface, there is no aerodynamic data. And I now have a runway at A&M outside my high bay, and I'm going to run this thing. And I'm going to get some aerodynamic data. I'm really excited about that. The students are going to have fun with it. There's going to be the Magnus effect. It'll push the ball to the ground, and it's going to be a really interesting series of experiments. The gyro and the inertial control, especially when it bounces and comes off the ground, it has everything it needs to be able to stay straight. So I'm going to save some time for questions, and I just want to leave with this thought. This is my students' motto for the project. Be the ball. And we're going to have fun with it, and I'm really excited about it. And we're going to be doing some much bigger things, for the future of robotics in the Texas region. But we're going to have some fun too. And with that, any questions? And I want to say hi to Professor Al Mock, who was on my PhD committee when I was here at UT Austin. I think you were on my wife's PhD committee too. So hi, Professor Mock. He remembers me when I didn't even have a beard. So questions?
The wear and tear of these kind of devices, right?
Yes.
The lifespan, right?
Yes.
What kind of it's rolling in two directions, right? So
right.
is that
so,
could it match a wheel of a car at a certain point or something?
So a wheel is amazingly tough. If you think of, and it took 100 years. If you think back to 100 years ago, cars were popping tires. They had like 4 spare tires on the back of their car when they'd go across country, and they were constantly repairing them and fixing them, and it was a problem. But we've gotten to today, the pneumatic tire is just a marvel of simplicity and ruggedness, and takes a beating, but you still carry a spare. I'm thinking this is so cheap, it drives till it pops, and then you're, deploy your sensors and end of life. But I think clearly the little rubber ball we bought at Toys R Us was totally wrong. So other anything else? We should talk.
And
yes.
I'm just wondering, do you need any kind of touch?
So let's talk.
Okay.
And we have total control of the pressure. The design of the robot can adjust its pressure within it.
I'm talking about the pressure sensors mounted on the outer surface and providing perceptions.
Let's talk. Wonderful. Right? Yeah, thank you.
Yeah, okay, thank you so much, Professor Ambrose. Yeah, it's a very interesting talk. And next, we will, if we have still time, we will have a Q&A session afterwards. So feel free to ask questions afterwards. So so next, I'm happy to introduce Professor Yu Xiang, and he's so from UT Dallas, and please take away.
Hello everyone, my name is Yu Xiang. I'm an assistant professor from the UT Dallas, and today I'm going to talk about closed-loop 6D robotic grasping of unseen objects. So the first question I want to ask is, why is robotic grasping challenging? We can take a look at the following example, right? We can have this robot pick up this mug on the table, then it seems like grasping is really solved. But the problem becomes much more challenging if we consider there are many different mugs the robot needs to pick up, right? The mug in the shelf, in the clutter table, in a bin. And also need to consider task diversity. The robot not just need to pick up a mug, but also use a mug to do some tasks, right? Depending on the task is making tea or coffee or cleaning, the grasping should be different. So the combination of environment diversity and the task diversity really makes the problem really challenging. So in order to tackle these challenges, I believe the perception, planning, and control loop is really critical. Here we have these robots that want to do some tasks in the real world. So first of all, the robot needs to perceive, to understand what's going on in the real world. In the example of using mugs, the robot needs to recognize all the different mugs. And after that, the robot needs to use the perceived information to do some planning. And this planning depends on the task. For example, if the task is making tea or coffee or cleaning, the plan should be different. So following, after that, the robot needs to apply control to execute the generated plan, right? And this action will change the world, so the world change. Then we need to have this closed loop. The robot should consistently perceive, plan, act in the real world. And more importantly, I believe learning is playing a very important role here because robots need to learn various skills in perception, planning, and even control. But today, let's focus on the task on 6D robotic grasping. And 6D means that the robots need to grasp in different orientation and location. This is in contrast to top-down grasping, where the robot just need to go down and grasp objects. So in the traditional way of a model-based 6D grasping, right, in perception, we can tackle this problem called 6D object pose estimation, where we use a camera to estimate the 3D location and 3D translation of the objects. And then we can set up a planning scene for motion planning. So here you can see you can detect these objects and the robot can plan trajectory for grasping. And after that, we can apply, for example, place and control to enable the robots to follow the planned trajectory and eventually grasp these objects, right? But the drawback of model-based approach is, first, we need to have a 3D model of these objects. And this is not a trivial task to obtain 3D models of all these objects. And also the execution here is open loop, meaning that once the plan is generated, the robot just executes the plan to the end. There's no feedback or perception or replanning during the loop. And open loop is prone to errors in perception or even in planning. So recently, people are focusing on the problem of how to grasp unseen objects. Right? Previously, we needed to have 3D model, but in this case, for perception, we can have unseen object instant segmentation. That means this approach can segment unseen objects. These objects are not seen during training, but the algorithm can still segment it. If you have an RGBD camera for each segmented object, we can have a point cloud. Then there's some approach they can plan grasps from the partially observed point cloud. Once the grasp is planned, then we can also plan trajectory to reach one of the grasps, and finally the robots can grasp objects. But again, in this pipeline, the problem is open loop execution. There's no replanning or perception during the execution, and this can cause a problem again. So in quarter last year, we proposed this approach called try to learn a closed loop control policy for 6D grasping. Here our goal is to learn this policy that's represented by a deep neural network and take a state as input and output some action. Our state representation is based on the segmented point cloud of objects. In this example, we can segment this t-shirt and get the point cloud of the t-shirt, and this is our state representation. But for the action, that's the relative 3D translation and 3D rotation of the gripper. And after that, once the action is applied, the state will change because this camera is on the gripper, right? The camera will move to a new location, will get a new image. So from this example, you can see the robot is following this green gripper. That indicates the next location the robot needs to take. And eventually, the robots can grasp this t-shirt on the table. And this is a closed loop control policy for 6D grasping. So we can see we use unseen object instant segmentation for perception, and the policy is used for control. You may wonder there's no planning. That's true, because this policy basically encodes all the plan. The robot just need to follow this policy for grasping. Right? In order to learn this policy, we combine imitation learning and reinforcement learning. We can use a motion planner as expert demonstration. So we set up a planning thing in hybrid here. Then we can generate a lot of trajectories of this robot grasping these different objects, and this can be used to learn the policy. So here's a demonstration on the robots can grasp various objects using this trained policy, but the policy purely trained in simulation, but it still works in the real world. One main reason is because we use the segmented point cloud of objects, and that is better for the sim to real transfer. So on the right, you can see the camera image from the robots, and this yellow point indicates the segmented point cloud of the objects. And these objects have never been seen during training because we just train on simulation with some 3D shapes, but robots can still grasp the objects. And because this is a closed loop policy, right, we can also apply this policy to human robot handover. So in this example, the task is to hand an object to the robots, and the robot need to pick it. So during handover, also move around. Because it's a closed loop control, the robots can follow the objects, right? So what's actually happening here is there's a perception system that can estimate the human pose. All this red dot indicates the human body joints, so we can localize the human hand, right? Then after that, we can segment the point cloud of the object in hand, and these green points are feed into the policy to compute the control action for grasping. Here are two more examples of handover. So we can move around the objects, but the robot can follow. So very recently in ICAR, or IAO this year, we extended this policy to clustered scene grasping. We have a hierarchical policy where the policy first generates a plan. The plan is represented in a latent space, but then condition on the generated plan, there's a low-level policy that can generate action to control robots. So we can do this closed-loop grasping for clustered scene as well. And this paper will be presented in ICAR, so I'll talk to you there too. So lastly, I would like to take this opportunity to introduce my lab because I just joined UT last year. My lab is called Intelligent Robotics and Vision Lab. Our vision for robotics is we want to enable robots to learn skills. This can consist of skills in perception, planning, control, and learning. And we wish these skills to be generalizable and shareable. And generalizable means that these skills should be able to use in various environments, in various tasks, not just for a single task or single environments. And shareable means we want to share the skills for different robots. All the robots should be able to use the skills once we learn. In the lab, we also build a robotic system that deploys these learned skills, so we can test the system, the robot in the real world. And hopefully during execution of these skills, right, the robots can also continuously improve their skills and eventually to become much more better. So yeah, I think I finished a little bit earlier, but that's all the students in my lab. We have so PhD student, master student, undergrad student working with me. And I'm happy to talk to all of you and do some collaboration on this very exciting robotic field. Thank you. Can I have some questions?
Yeah, we have some 2 minutes left for the 10 minutes session, so questions.
Because of lack of touch perception.
Yes, basically we just.
To me.
Yeah, there's no touch sensor on the robot gripper. We just apply a fixed force. That's why it's with the objects. It's interesting to combine touch sensing as well.
How do you in the robot handoff? How were you making sure that it didn't grab his hand or that his fingers weren't pinched in the process when handing the object off?
Right, that's a good question. The robot doesn't know where's the hand, but we segment the point clouds of the objects and then just try to grasp the object. But in most cases, because humans try to collaborate, right? You hand the objects in a way where the robot won't grasp you. So, but it's interesting to see, try to avoid. Sometimes it may move a little bit further, so that human may be afraid of that. So it's an interesting thing to study as well.
Yeah, I think, yeah, so we're...
Thank you.
Yeah, we're good. Yeah, thank you very much, Professor Xiang. And yeah, next, Professor Nick Fei. Yeah, so Professor Nick Fei is from UT Austin Mechanical Engineering. Yeah, so he's going to give the next spotlight.
Oh, there you go. Perfect. Yeah. So thank you, UK and Joydeep, for the invitation to present this year. So very excited to be a relatively new faculty at University of Texas at Austin in mechanical engineering and the Texas Robotics Center. There's lots of acronyms we're going to hear today from different lab names. Ours is the SOM lab, so we study systems that augment fluid mechanics. I thought I would be presenting after the Mahi lab. I don't know if Marcy presented early. I know we'll hear from the arts lab later. There's the Hero lab here. There's lots of acronyms. And allow me to first put the Texas in this Texas Robotics Symposium. So the reason I chose that is I actually grew up not far from here in a small town called New Braunfels, Texas. So grew up on a farm, some stock farm. That's my mom's maiden name. We've got all the components of a good country song here. We've got the cattle, the field, the sky, the grass. We have my truck. Actually, this is the second truck I've ever owned. I'm missing the dog, I guess. But you know, this is a little bit of a frame of reference here where some of my work and interest in mechanics and engineering started working on farm equipment, tractors, and sensors and things of that nature. So came here for my bachelor's and master's and PhD in mechanical engineering, studying first neuromuscular biomechanics, getting into some physical human machine interaction more from the dynamics perspective, and started as a postdoc in Chicago at Northwestern's University Shirley Ryan Ability Lab, where we really delved into what I would consider to be more robotics field, so myoelectric control, semi-myographic control, and some forms of machine learning. And we study typically prosthetics and orthotics interventions for people with limb loss, and we focus primarily on the lower extremity. So this field is often considered to be bionics. So if you think about, for example, a transfemoral amputation, a person with a transfemoral amputation, a mechanical device that's intended to replace lost biological function. Sure. Just pull it up here. Sure. That's a lot to ask of a mechanical system to have an appropriate sort of interface to the user physical interface, but also an interface where you can sort of pull information and interpret that information about someone's intentions. You would want to recognize in advance what someone would like to do. And then even if you knew what someone would like to do, how do you deliver that within a control system in a biomechanically appropriate way? That's difficult to do because most of that depends on the environment someone is in. So whether they're on level ground or stairs or in an unknown environment or something that they know very well. And even if you did all of that correctly, you know, the way that a person, this super important gray person behind this complicated system, the value that they place on biomechanical objectives is really specific to them and the way that they move. And so you can kind of over-engineer these devices without actually not considering what a user may want. So I would say the first bionic leg here, this is a postdoctoral work with Levi Hargrove and Todd Kuiken, who were the first to really tie the neuromuscular system of a person to the control system of a motorized lower extremity prosthesis. And this system was published in 2015, so it's been around a while, but it's still one of the best examples of a system that responds to someone's intention. It predicts at every toe off and heel strike the next terrain, adjusts its control system accordingly, and even during seated postures, first people can reposition their device. And to do this, we interpret myoelectric signals and mechanical signals that are embedded within the device. Myoelectric signals from the person's device, from the person's leg. So if we compare that then to maybe an outside of the lab environment, so this is a coalition that I helped to start in the DFW area during my first faculty position called the Adaptive Sports Coalition. This is a US Olympic amputee soccer athlete shown in the top on the left here. This is amputee soccer in adaptive sports competition at an Olympic level. What do you notice? Where are the prosthetic devices? You think these people need crutches to walk normally? No, actually the rules of the adapted sport are you have to use the crutches. You can't kick the soccer ball with your residual limb. That's against the rules. And so one of the reasons people do that, or these rules are in place, is to level the playing field, right? Every person has a different prosthesis. But another sort of, I think, a more telling example is that these devices just really aren't that great at functioning in real world scenarios outside of the lab. And recreation is one example, and the community and the workplace are others. And so another sport here is floor volleyball, where you have to stay on the floor, right? In order to just totally eliminate your lower extremity. This is one of the, the most common adaptive sport is wheelchair basketball that you're probably familiar with. So I think there's a really huge opportunity here to sort of reshape what it is that prosthetic devices can do, should do, using advanced robotics. So our lab really focuses on a few core challenges in related to ambulation. One is that ambulation is not discrete. There's continuous time, continuous terrain. There's unknown and known scenarios that the devices need to operate in, and that humans themselves are specific in the way that they move. Everybody has individualized gait patterns, their own intentions and value they place on certain things, but their shape too, right? If you think about putting a prosthesis on someone, that can be very personalized. So for the last time that I have here, 4 minutes, it looks like, I'll talk about a few quick student projects. And so one is funded by the NRI 2.0 program, was a recent graduate from the lab, Caitlin Raby, and the University of Utah, where we looked at different forms of muscle-based sensing called sonomyographic sensing to inform how a motorized prosthesis should behave. And so these are signals of your quadriceps muscles imaging transverse across multiple quadriceps during a weight-bearing, sort of going up and down stairs and ramps and on a treadmill. And these oscillations are what happen from heel strike to heel strike during gait. We can look at these signals, the intensities of these images, their temporal nature, the information that's from superficial muscle all the way down to deep, which is shown here. And we can predict, for example, we could log, because ambulation is cyclic, we could log these signals during the stance phase of walking and predict what the swing phase kinematic should be on multiple terrains, predicting future trajectories. On the other hand, we could log these data during the swing phase and predict future torques that are required within the device or joint moments during the next stance phase. And so we could use this for motion planning, and we'll demonstrate this in an ICRA presentation this year. And the second area is that really looks at the physical interface between prosthetic devices or robotic systems, wearable robots, and the human itself, and the way that that interface is defined and can be optimized. And so this is a new student in the lab, Marissa Piritano, a future graduate who will be graduating in May, and some local partners that we're trying to really get this project going and funded through primarily the DoD. And so for this, we're looking at the transfemoral residual limb itself and how different technologies interact with it. Because even if you had a robotic system that was really amazing, if you had a really sloppy connection or a suboptimal connection to the person, that can really constrain or even enable, really enable, if you had a great interface, what someone wants to do. I'm just going to kind of skip ahead a little bit. So we know that local properties of the limb itself can change the way that someone does steady movements, but also transient movements. So this is kind of a bird's eye view of the center of mass trajectory during a timed quick stepping task. And we show that when you can actually reshape the soft tissue composition of someone's limb to improve their mechanics. Not only the local properties of the limb, but the way that someone controls a prosthetic device. And so what we're doing now is to really help inform in this area standard of care surgical planning. So these are all patients who have excessive soft tissue within their residual limb, and they're in pre-op. So this is a plastic surgeon sort of plan for what that surgery should be in terms of removing soft tissue. So what we are doing is to help guide that with an optimization framework to basically present, based on medical imaging and mechanical modeling, what are some optimal areas on that limb that should be there, or suboptimal regions of the limb that should be removed. And so these are some things we've demonstrated on a couple of patients, and I'm acknowledging here a local partner in Texas, Yassine Dyer, who's Vice Chair of Orthopedic Surgery and Physical Medicine Rehabilitation, and obviously the students' work. And the last quick area I'll highlight are personalizable exosuits in continuous terrain. So this is Ross Newman's work. There are no local partners who developed this completely throughout his PhD, and he is really looking at hip flexion exosuits. So exosuits, what are they? They're soft textile-based orthoses that have very few kinematic constraints as opposed to conventional sort of hard robotic systems that are worn. They're highly configurable, and they're comfortable. But because it's form-fitting, it is actually functionally dependent on the form of the user. And so this is the last slide here, ROS is basically looking at how certain characteristics of someone's BMI, or their size, or their sex, their shape itself, can be used, information about that, as well as their individualized gait patterns can be used to predict what are optimal configurations for even an adaptive system, not just a completely passive system, how they can be scaled for multiple joints, and how, basically, I guess what I'm trying to say is, designing control of soft exosuits. And so I thank you for your time, and if you have questions, feel free to email me or any of the suits. Thank you.
Okay, cool. Thank you, Professor McVeigh. And next, we are going to have the last speaker. Yeah. Maybe we will have like maybe 5 to 10 minutes at the end. For questions. Yeah, cool. Thank you. So next, last, we are going to have Dr. Ken Elimelech. Sorry, if I pronounced it correctly. Yeah, so please take away.
All right. Yeah, I'm a little shorter. Not that short. Is it okay? Hello, everyone. My name is Ken Elimelech. I'm a postdoc at Rice University, working with Professor Lydia Kavraki and Professor Moshe Vardi. Today, I'm going to provide a brief overview of the latest line of research that we recently started in the group, which revolves around task and motion planning, or how to improve the efficiency of task and motion planning by utilizing the notions of abstract skills. And thankfully, Lydia has done a great job introducing the task and motion planning problem earlier, so we are all already excited and motivated about this topic. No? All right. So to get a little more concrete motivation, we can look at the following example, and we can have a robot here that operates in this manipulation domain, and we have in this domain 3 boxes, and we have 3 cans. And at first, the robot is tasked with stacking the 3 boxes in this pyramid configuration, and after some intense calculations, it manages to find a successful plan to perform the stacking. And later on, we give the robot another task to stack the 3 cans on the other side of the table. So for a human observer, we can intuitively say that these are 2 related tasks and that the solutions would be related. But we cannot exactly reuse the same plan that we had beforehand, because we need to grasp different objects that might involve different grip rings, and we need to also perform it on the other side of the table. So we need to somehow automatically adapt the plan that we had before if we want to reuse it. So the question that we're concerned with is, how can we automatically transfer knowledge from successful solutions of previous tasks to more efficiently solve future tasks? So let us first define what is this knowledge that we want to transfer. So a solution to a task is, in this case, a task plan, a discrete plan, right? So it can be represented as a sequence of states and actions. So we have initial state, we perform an action, we reach to the next state and perform another action, and so on. And typically, when we think of how we can reuse a plan, we think of how we can take the sequence of action and reapply it in another context. But in our work, we realized that it might be more flexible, and we might be better off by looking at this roadmap of states. So instead of looking at the actions and transfer the actions, we look at a sequence of states and try to transfer those into our new domain. And after I transferred successfully this roadmap of states, I can just, in my destination domain, easily calculate the actions that are required to follow this road. And this is especially relevant, for example, we have 2 robots that have different action sets. One robot can pick and place items, and one can only push items. So we will not be able to just take the action set and transfer it. So, but with this technique, we can still take the roadmap and adapt the actions appropriately. So now that we understand what we want to transfer this roadmap, we can understand now how to perform this task. So we're doing it using the concept of abstraction keys. And abstraction keys been recently introduced in our work that's been will be presented in Wafer later this year. And abstraction keys are generic tools that allow us to automatically adapt and transform states, so the states in the roadmap. And every abstraction key operates on a specific property of the state. So if our state specifies what type of object we're operating on, then this is a property. If it specifies the location of an object, this is a property. A color, it's a property. So to transfer, to maybe change each one of these properties, we will have a different abstraction. And in practice, an abstraction key is based on a pair of parametric functions. So we have a projection function to take the states and remove this property that we're concerned with and takes us to an abstract state. And then we have the inverse function that takes the abstract state and just plugs back in this value that we removed. So we can see here, for example, in the figure we have a state and we have one part of it that is like a color, specifies the color of an object, it's blue, and by going to the abstract state, we just remove the color blue. And then we can return by perform the reconstruction. And this technique provides us with a very systematic and intuitive way to perform transformation of states. We simply remove the property that we are concerned with by applying the projection and then reconstructing with another property. So for example, here I change from blue to red. I will first remove blue and then reconstruct with red. So, and if we're talking about the same example from the beginning that we had boxes and cans, then I can remove the explicit type of object that it's a box. I will just have an abstract state that talks about any object, and then I will plug back in the can. So this way I can take a box stacking plan and transfer it to can stack. So this projection we can, as I implied, we can just apply it to all the states in the roadmap such that we get an abstract roadmap. So every time I successfully successfully solve a task, I can, instead of just saving the plan as it is, I will first project it to an abstract domain, and then I will save this abstract roadmap, and we refer to this abstract roadmap as a scale. And then, once I face a new task, I will just query my library of all the skills that I accumulated and see if any of them can be applied to my new task. What I'm practically asking is, can I take this abstract roadmap and find a parameter to reconstruct it such that this new plan is applicable to my problem? And this techniques allow us to avoid domain-to-domain coupling. So we always just save this abstract representation, and even if we have new domains that we have yet to see, we can just reconstruct it appropriately. All right, so maybe we can get a little bit of clear understanding by looking at this illustration, this domain. So we have a discrete grid maze here that represents any discrete planning domain. It doesn't have to be navigation, but we have a start state and a goal state, and we have obstacles. And the solution here is we're looking to find a path from the start to the goal. Right? And next to this domain, we have also a library of skills that we accumulated from solutions of previous tasks. So every one of these just represents a roadmap, and the abstraction key that we use here, this allows us to take any of these shapes and stretch it and rotate it and place it anywhere that we want on the grid. Right? So as long as I preserve the shape, I can just try to place it on the grid. And this can be done automatically with the abstraction. And what we are asking here is, can I take any of this shape and stretch it or rotate it or adapt it in a way that the both ends of the roadmap will align with my starting goal? And this means that I managed to match the skill to the starting goal. So we can see here some bad matches. So we took the skills, and you can see that some of them only align in the goal state, some of them only align in the start state, some of them hit the obstacles. So these are all bad examples, but it shows how we can adapt the skills that we have as abstract skills and put them on the grid. But actually we don't need to check all the configurations. We can symbolically, if the value, the right parameters exist, we can find them symbolically. So in this case, if we look at the purple skill, you can see that we were able to find the parameters to match it to our plan. So we can see that we rotated this roadmap and stretch it out a little bit, and we were able to hit the start, code the start, and the go. So in this case, this is a successful match. And after I've done this, I can just easily plan the sequence of actions that is required to follow this roadmap. And this will for sure be more efficient than simply blindly searching the space because we have a roadmap. So this is the general concept. Try to be not too specific. Here are some ideas that we started to pursue and we will pursue in the future. So taking this idea and putting it in motion planning, so continuous domains, composing skills in roadmap, learning skills, learning abstraction keys. And if any of these sounds interesting to you, then you're welcome to talk to me because we're always looking for more people to collaborate with. And actually right on time, I have 2 seconds, 1 second, 0 seconds. Thank you.
Thank you so much. Okay, now, yeah, so because they're still setting out the launch out there, so we're going to have the Q&A until 20. So like including Ken and also David and also Nick who didn't answer. Yeah. So I guess just not Professor.
Thanks, Ken, for the really cool talk. I was curious to hear your thoughts on how do you define these properties which you can add and subtract from a concrete plan to abstract them?
So for every property that you would like to change, you need a new abstraction. So the abstraction keys themselves need to be designed by a human, but once they are generic enough that you can just choose the property that you want to change. For example, the type of object, the locations, and just have this library of abstraction keys that we can automatically use. So you just need a human to specify which properties can be adapted, and then the system can automatically.
Okay. I was mostly thinking of how do you come up with the properties, but it sounds like you answered it that the human defines the properties, right?
Yes.
Okay.
So a human define a property and just create an abstraction key for it.
What happens if there's something like additional obstacles suddenly like added into the system? Do they you have to replan it in a certain way?
So that's actually a great question, and it actually shows the strength of this method. For example, let's say that we reconstructed the purple plan, and one of the states in the roadmap has hit an obstacle. Then we can simply skip this state and follow and plan to the next state. So the roadmaps are adaptable, because even if I take one state off the roadmap, it's still a roadmap. And if I was trying to transfer an action plan, so the action sequence, once one action fails, the rest of the plan is invalid. And in this case, it actually shows, and thank you for the question, that it's more flexible and we can overcome such.
Yes.
Thank you. Nick, I like...
I can answer on their behalf.
Sorry. I like that last project you showed where it was about dynamic systems, but parts of the system that are more static than others in the way that the legging or the wrapping or strapping or whatever you want to call it are wrapped around there. It reminded me of a project that Rob probably remembers from NASA with gloves, redesigning gloves. And I recall then it was much more of a, just kind of let's play with it, see what happens kind of deal where they put tape on their fingers and see how the tape changes. Kind of stay static.
Sure. Yeah. So, I mean, most typically, like even just doing traditional motion capture, you would identify, with reflective markers, typically those reflective markers are placed on what we consider to be like bony prominences. So in the front of the pelvis, the ASIS, PSIS, your hip, your greater trochanter landmarks, things like that are actually, relatively uninfluenced by skin motion and things like that. And so when you think about an exosuit, for example, that's why, a waistband, something that mounts on the waist, is a great idea because it can sort of mount there close to those bony prominences. If there's any sort of excess adipose, hang over a little bit those belts. Yeah, I think that's what you're asking primarily, is that, right?
Yeah,
as opposed to sensitivity to different terrains.
Yeah.
Sure. Right. So.
Yeah.
Yeah. Yeah. Mm-hmm. So the length of those actuators, for example, in a passive case, you could just let the hip flexion alone, extension, change the length of that passive actuator, right? Because it's spanning the hip. But then the moment arm that tension creates about the hip is also a function of the configuration of the hip. And so that's a non-trivial thing on its own, but we are currently investigating sort of non-static proximal and distal attachment points to basically keep systems to be passive, but to move them a little bit, right? When the device is unloaded, let's say for certain terrains, where you might be able to store that elastic energy due to frontal plane motion, so hip adduction, and then maybe return that elastic energy in the sagittal plane for hip flexion. So we are investigating that, using that system to do that as well. Yeah. Yeah, thank you for the question.
Okay.
We have not. There are people who have sort of hybrid finite element models, like kind of multi-scale basically, where you're doing finite element models of soft tissue of the foot, the bone within the foot, and then you combining that with rigid body musculoskeletal simulation in a similar way, where the models sort of talk to each other, kind of like how we showed in the last aim there. So it can be done, and typically that's done first with like system identification, where you're pushing on certain portions underneath the foot, and you're then characterizing stiffness, dissipation, that kind of thing, and then informing then your finite element model yeah. So people have done that for sure, and that data is out there actually, kind of publicly available. People are very interested in feet because of like diabetics, for example, and the blood flow within the foot and pressure concentrations that exist on the bottom of the foot. But I think you're asking more from a space perspective, right? Sure. Right. Right. Yeah, that's a great idea. Mm-hmm. Shape of the femur as opposed to the distribution of soft tissue. Yeah. Yeah. Mm-hmm. Yeah. And one thing I didn't talk about too, but the amputation surgery itself, so how muscles are anchored, muscle lines of action change, the way that they're sutured together. Sometimes muscles are sutured to muscles, sometimes muscles are sutured to bone. And there's different surgical techniques that are associated with that would change the way that someone can actually activate their hip. So you think they still have their hip, right? It should be good. But because they've had a surgery, that's all messed up too. And so, but if you have a nice knee and ankle prosthesis, an active system, you could potentially compensate for impairment of the hip. And so that's a question we're interested in as well.
Well, thank you. Thank you so much for the...
Cool. In the interest of time, I suggest that we break for lunch so we can have lunch. But let's continue these discussions outside over lunch, definitely. Thank you. We'll be back at 1 for the next keynote session. And lunch is on the 3rd floor. You can take the staircase up, get lunch, you can spread
go. So you see the
Open now.
need an introduction, but I'm going to do it anyway. Okay. So, and she is a visiting professor of computer science and engineering at TEROS, where she directs the Center for Robot-Assisted Search and Rescue. And Robin is a founder of the field rescue robotics and human-robot interaction. She serves many executive boards and national academies and the defense boards. And Robin is most famous for putting robots into disasters. And, actually, I got to know her research because she gave a wonderful TED talk about her work on using robots in disaster relief and disaster rescue. And I think the TED talk gets millions of views. Right? So it's really cool. As you can see from Robin's first slide, and you're gonna expect many cool robots and many cool robot videos from her talk. So without further ado, yeah, Robin, forward to yours.
Well, thank you. And as we say at Texas A&M, howdy. So robots, COVID, Texas. Well, we're here in Texas. We got a lot of robots, and isn't it nice to be seeing each other again in person? And for those of you on Zoom, sorry about that. It's great to be back in person. It's great to be back in person. And so let's see what's happening. All right, and as you said, I do disaster robots, but I'm going to be talking about robots used for COVID for the past 2 years. And that may seem kind of a stretch, but if you disasters, we use the all hazards approach. A pandemic is just another disaster if you're an emergency manager. So we'll look at that. So we started right after the WHO, World Health Organization, declared the pandemic back in 2020, in March 14th. And there was this cute op-ed said, where are the robot overlords when we need them the most, right? Because everybody's locked in, nothing can be done. And so we said, game on. We rose to the challenge. Where are they? And so for 2 years, we've looked with funding from 2 different National Science Foundation grants looking at different things. And we have found that there is at least 420 discrete instances of robots being used for things directly because of COVID that wouldn't have been used before in 53 countries. And we've done analysis by the work domain, by the date, by the country, the modality, morphology, technical maturity, legal issues, all of these things, and we have a great team that's still working on this. Dr. Angela Clendenin from Public Health, Dr. Paula DeWitt from the law school, and Dr. Jason Motes from the Emergency Management Extension Service, and some wonderful, great students. So I'm not gonna be able to talk about all of that in 30 minutes, but let's go for it. Let's see what we get. So 420 instances. How do you get data on something, particularly in year 1 when everything was so new? So we went to social media. We also monitor all the scientific literature. Our rules of engagement were pretty straightforward. If they said they were using a robot, even if it was a Lego robot that was being used as a hand dispenser, we counted it as a robot. But it had to be in the field. It actually had to be in the field. It had to have proof that it was actually being used by real people for at least 1 day, and we would keep that in there. Now, one way to think about pandemics is to think about them from a medical viewpoint, and I was part of a team that did think of it that way: prevention, detection, diagnosis, treatment, and recovery. And that is great if you are trying to do medical robotics. But what we wanted to do is we're seeing it beyond medical. And so what we did is use a clustering technique to look at socio-technical domains. Not just medical would be one, but let's look at public safety, things like that. And so you start breaking it up with the way Amazon might use robots for warehousing is going to be different than a hospital is going to use robots. It's a different set of constraints, a different set of monetary factors, a different set of regulations. So we looked at that. So year 1, so the first year, January 24, 2020 was the first time we have any reports of a robot being used. It was in Seattle, one of the Seattle hospitals. Somebody came in, they thought they might have Ebola, something bad, and they said, nope, send the teleoperated robot in to start the analysis there. So what we found in year 1, 340 instances in 48 countries, and the countries are in blue. The top 8, and we'll come back to this in year 2 to look how that changes: US, China, India, Great Britain, Italy, South Korea, Spain, and Singapore was tied with Thailand. Singapore had the first use, so we broke the tie that way. Y8, 8 works really great on PowerPoint slides, on being able to keep up with and work with. But you can also see how it tails off pretty quickly after that. All right, so here's what we expected. We expected pretty much everything was going to be clinical care. Stuff in the hospitals, a little bit of public safety, the public health department doing the quarantine enforcement, that sort of, and a little bit left over. No, this is what we got. Clinical care was about a quarter. Public safety was actually uses reported were more. Now, you know, the data's noisy, we've got all these other things, but overall as a trend, kind of interesting. Continuity of work in education was large, laboratory supply automation, quality of life, and the non-hospital care. Quarantine camps were popular in Asia, common mechanism for us in the United States, and in Europe, taking care of people in elder care nursing homes. Was the purple. So that's what they look like. Public safety was the big winner, and the intensity is relative proportion to the number of instances. Quarantine enforcement, yes, police all over the world were sending drones to find people having a good time during the lockdown and to yell at them, because now you can buy a little attachment to do that, a little speaker. Okay, so that was the big one. And the second largest was to take agricultural drones and start spraying everything. Entrances to subways, park benches, things like that. And that persisted until the World Health Organization said, you know, the drainage, you're killing all the fish and wetlands. Could you please stop, because it doesn't work and you're having environmental impacts. And everybody went, oops, never mind. Okay, clinical care, disinfecting the point of care. World's dumbest robots is an autonomous robot. You either reel it in or it's got just enough slam that it can make it in a door. It sits there for 45 minutes, zip, 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 kills everything, about 99%, doesn't catch anything that's underneath. But one person can come in, wipe the rails. It's pretty obvious what it is. And of course, hospital rooms are in fact pretty sparse. I mean, we've all seen how there's nothing in there. Speeds up, wonderful help to help turn over rooms, to help keep things going, to help the surge, particularly when the janitorial staff was also getting ill and not being able to show up for work. Observational telepresence, iPad on a stick, right? You're seeing those flow, and those became public. But delivering an inventory, you're thinking about, look at the beautiful work here at UT Austin with Moxie, coming out of Andreas Thomas's group. So we see all of that. The big surprise was continuity of work in education was so that this is people, individual people are non-traditional robot users suddenly acquiring robots. So sure, every school that could thought about it, large companies started building the disinfection robots, okay? Same thing with telepresence, but we also saw a huge spike in warehouse and process automation for worker shortages, saying we've got to do this because we're running out of workers. It's not that, you know, it's because of COVID. It wasn't inevitable. Laboratory and supply chain automation. We had thought this was going to be the big other. It wasn't. Laboratory and supply chain automation, primarily delivery, and that is delivery of samples. You don't put your lab to run all the samples next to the nice hospitals in the nice part of town. You put those over the warehouse district by the airport over there, and so you lose a lot of time shuttling back and forth. Drones were great. They worked wonderful, particularly since everybody was in lockdown. There was nothing to hit, so all the aviation agencies in those countries said, sure, go have at it. Handling infectious materials inside was another one. Quality of life. Delivery of food became important as that, oh, we're just going to be down for 2 weeks. You know, kept stretching on. There was a report from a set of people in the UK that said they thought at the first of it, they thought the idea of delivery robots was the stupidest thing they ever heard of. It's just this one of these Silicon Valley things. And then when they started, everybody started running out of milk for the kids. And even that little small one that was coming around to the neighborhood, 2 thumbs up. They loved it. Of course, there's all sorts of fun things people were doing. In New York, a person had met somebody he wanted to date, but hadn't asked him for a date, but she lived across the street, so he flew his drone over to talk and ask them for a date and promised that the first date after the lockdown would be. And another one is somebody walked their dog with their drone from their balcony, and just sure, okay, got it. And the non-hospital care, that delivery to quarantine, we saw a lot of that. You're there, you're in this hospital, in a hotel room, it comes to your door, beeps, you pull it off, press the button, it goes to the next one, beeps, and so on and so forth. Big thing here, I think, is really cool, not replacing people. These were, public safety was to enforce the public health policy. The clinical care was all about protecting the healthcare workers and handling the surge and maintaining and keeping a hospital going. Continuity of work and education, again, protecting the workers and the customers, trying to make up for shortfalls and worker shortages, and handling the surge, because a lot of now all of a sudden everybody had to get these online orders through. Quality of life was quality of life. Laboratory and supply chain automation, again, handling the surge in demand for all of these samples to be run. And then the non-hospital care, again, trying to get, Italy did a very good job of trying to work with the elders. So there's a lovely paper on that. Now, if we look in terms of morphology, the ground robots, majority, aerial. Ooh, look how many aerial, very sizable amount of aerial robots, 2 marine robots, 1 to go out and check oil rigs out in the North Sea, and 1 to do something similar here in the United States. So that was really interesting to see that split. And we saw 29 discrete use cases. So they would have some difference in the workers or the interactions, as well as the cost, the purpose, things like that. So we saw that. And if you look at those work cases, you can kind of glom them together. 85 instances at about 14 of the cases had something to do with disinfection. And notice you saw that the disinfection was autonomous for clinical care, but those drones flying next to buildings and slightly inside the overhangs of a subway, those were all teleoperation. And then delivery, it was autonomous, but it was autonomous under conditions that we don't have right now. Telehealth, teleoperation, because the point isn't to automate health. I mean, I was pretty clear if my dad had been sick, you came at him with a robot and there's not a person talking to him or anything like that, he wasn't going to put up with it. And they found that out in Italy, where one of the robots, they actually started thwacking the old people, were like hitting at it when it came by, saying, where's the doctor? So, but teleoperation is there to allow, to protect the healthcare workers to have a good interaction, to enable them to be humane and to do those things. So that's important. If you look at morphology, there were a lot of humanoid robots among the ground robots. There were a lot of robots with manipulators. There were very few humanoids with manipulators. So basically you had things that looked human, kind of that social engineering kind of cutesy look, not necessarily form, fits, function. So that's interesting to think about. Another thing that we popped out in year 1 is there were 61 explicit cultural and ethical concerns. So some of the legal things. So public safety 1, yay team. Public safety used those drones. People were worried about privacy. They were worried about unwarranted surveillance. They were worried about ethics, things. Clinical care, an interesting, with some of the cases and things like, you're certainly worried about privacy, you're worried about, but there's the idea of unproven claims of effectiveness. So the disinfection robots, big win, right? So everybody wanted them. A lot of countries now, you can't ramp up. The 2 major companies, one here in Texas and one in Denmark, couldn't ramp up fast enough. So what's the solution? We'll build our own. I mean, how hard is it to put some lights on a mobile base? Well, the lights aren't just lights. They have reflectors, there's a duration of time, there's all these sorts of things. So you can, one sweep, you can violate intellectual property law and you can get it wrong. So that wasn't, that's something to worry about, right? It's like if you have a gap, Do you want rapid manufacture? How do you protect these things so you can catch it from both sides? All right, let's see what happened in year 2. So in year 2, so now this is the overall through there for the year 2. Now let's look at that slightly and see that 80 instances in 25 countries. So before we had seen in year 1, 340 instances now. So we're not getting as many news reports. We're mostly getting scientific, the novelty has gone down, but still there. But anyway, those are the 25 countries. So we've seen, you can see some things like Russia, things have dropped out there. But what was interesting is we got 5 new countries, and mostly in the East and Middle East. So that's also an interesting thing to look at. We're looking at it from diffusion of innovation. And looking internationally, you started out strong, you kept on going strong. Okay? Singapore had been tied with Thailand. It was just, in year 1, and then Thailand slightly pulled ahead. But the US, China, India, Italy, the big players just in there. So there is something to be said in terms of policy. If your country, and this also is related to whether or not you had a national robotics policy. So that helps to see how useful this is going to be for your country. Now, if we look in terms of the change in year 2, just year 1 versus year 2, not overall, you see that the clinical care went down, the public safety proportionally went down, but continuity of work bumped up. And that kind of makes sense. We've survived. We've got the public health crisis sort of under control. But what about us? This is getting old. What's in it for us? What do we do? How do we get our lives back? And so that kind of makes sense, right? And then, and I like to think of the total lack of non-hospital care as a stunning graphic admission that in the United States, which was, in China, we don't care about old people, whatever. Nursing homes, forget it. All right. What's also interesting is that there were no new use cases. We didn't see as many instances. Some use cases had none, but we didn't see anything different in our clustering happen. So the big cases were the big cases, the disinfecting, the delivery, the telepresence. But what we did see, again, with those use cases is the shift to regular people. So instead of public safety and clinical care, which had been 1 and 2, continuity and work and education popped up to 1, moving public safety and clinical care to 2 and 3. Now, if you look at the international trends throughout the 2 years, let's see, let's see if the cursor works. Yes. Okay, so this is the epi curve, right? So you can see how and then it's gotten really bad. But here's through year 1. And this is not surprising. The first month right here is March. This is right when we're getting the pandemic declared. Everybody gets interested. And look, all the different domains: public safety, clinical care, continuity of work and education, laboratory automation, pulling a blank on the other 2. But anyway, isn't it interesting? It wasn't, first we're going to get a spike in clinical care because the healthcare workers, and then, we've got to do the lockdowns. So now we're going to get a spike in public health, and then we're going to get this. And then it's like interesting, the diversity of solutions that got adopted immediately within the first 3 months. And then we see, and not terribly surprising, within a month or 2, we've started to plateau. What you had, and this gets into technical maturity, which is a whole nother talk about technical maturity, but the majority of 73% of the robots used in the first year were existing robots being used in normal ways that just nobody had bought a bunch of them or put into service for this. So there wasn't a lot of innovation going on. It was like, oh yeah, those disinfectant robots have been used up in Dallas. Let's buy them now, quick, buy them. We should be using them too. Those types of decisions are what we're seeing. Same thing with the drones. We're seeing a lot of that. But then notice what happens. continuity of work in education starts off kind of slow, and then it but it's got a really good derivative, right? It's got a slope there going. More than anybody else of the other domains really isn't tailing off as fast as these other ones had. So that's something to keep in mind. If we compare with year 1 and year 2 in terms of modality, about the same. Public safety, lots of UAV, still lots of UAVs. The blue is for UAV, brown, the little brown side is a proportionate for ground robots, and then the goldy silvery is for water. Right, so clinical care, more ground robots. Continuity, a little bit more ground robots, but still about the same. What we do see a surprise is in quality of life, all of a sudden we're starting to get ground robots. And that may be because of a product latency effect. That ground robots are harder to get, they're more expensive, so the investment, more lag time, more lead time on those. And so that there could be something to investigate there. So to recap, year 1, we saw public safety led clinical care in numbers, but we had, even in year 1, a very surprising amount of public sector use. Public safety, clinical care, government are highly regulated institutional uses. Teleoperation was as valuable as full autonomy. And teleoperation, not because we can do autonomy, but teleoperation is because we wanted remotely to act remotely and be engaged in that loop. Public safety use of drones, ethical concerns and environmental concerns. And in year 2, leaders of adoption kept on adopting. The private sector use grew even more, and the ground robot use increased, again, possibly with that. So what does that mean? So we're looking at the year 2 data now. So we're hoping to get more analysis of that out the door soon. But hopefully that gives some idea of what happened with COVID and robots. But who cares? So what? What has this got to do with this? Well, I think the important things for us here in this workshop is that, first off, robots are happening. This is the first time we've seen public-private interest use robots. It's always been agencies or large companies over there. This is regular people using, regular people go, yeah, delivery's okay, that's fine, right, we got it. You know, this is the first time we're seeing this. So this could be that inflection moment. And then the other one is that everything we're doing here in Texas, across all the things we saw this morning, the things on the list to talk about today, that is all relevant. And it's relevant what we work together on for disasters, works for pandemics. And I promise for Luis to add this in, for refugees, for that crisis, that's another crisis. And if you're interested in that, I'm on the committee for the Robotics Autonomous Automation Society Special Interest Group on Humanitarian Technology and the things that we can do there with robots to help with that. But the big thing is, it's all about Texas, what we can do and how we can contribute. So hopefully we can use this wonderful opportunity to work together.
All right, thank you, Robin, for the very nice talk and echoing the theme for TEROS. So let's see if we have a question. Oh, Jody.
Cool. This is a really nice overview of what happened in the robotics sphere when COVID happened. I was curious if you could share some insights on the effectiveness of these robots and how that changed over time.
We're trying to figure that out. And so there's analysis, Dr. Clendenin's group in public health in particular, we're trying to concentrate on public health and public safety, since those were the 2 biggies, and to go back and see what the effectiveness were. And that's really hard. Public safety hates to put anything on the record. And okay, so remember that part about surveillance and privacy in the 61? Yeah, and most of that being, but well, many of those public safety has realized they don't want to talk about their drone use because it's a no-win scenario for them. But the clinical care, we're starting to see how they make their decisions and things and the effectiveness. And they were like, in the story goes something like this. Yeah, it was working for our sister hospital, but we had never gotten around to buying them. And then we bought them and we liked them. And of course, they're fine. They're using it. We're using it. Yeah, kind of thing. It's like, no big deal. Why are you bothering us with it? It was a no-brainer. So I think that's one thing to take away from it.
thank you for the awesome talk, Professor Murphy. So what do you think could be like, other than the negative responding with robotics to deal the negative situations like COVID, pandemic, refugees, what do you think other than this could have, like we could have a catalyst that could increase the uses of robot other than the negative situations like pandemics and stuff?
Well, I work in disasters, so that's always a negative, and you always want to try to prevent disasters, right? Pre-disaster mitigation is important as disaster response. Disaster response is sexier, right? Rescuing the baby or something there. So let's try it this way. So you saw that majority of the use was around disinfecting. And the hospital was all ground robots. Where did those ground robots start? They started with Ebola. During the Ebola crisis, we had the companies being, how do we disinfect hospitals? Now, we didn't have hospitals get hit hard by Ebola. It was mostly confined to West Africa. We did, Texas, yay, we're #1, managed to take out not 1, but 2 wards of their, one of the hospitals up in Dallas with 1 person being infected. And so that hospital got really interested, and that was where Xenix came from. Well, by the time they had built the product, 18 months is your product development time? So by the time they had created the robot, pandemic was over. It burned itself out, had never jumped to more than a couple of hospitals. So there was but you know what? Hospitals every day have to deal with hospital-acquired infections. And that became the selling point. So 7 years later, when you get another pandemic, you've had these robots, they've already been in use for 7 years, people are comfortable with them. Some of the other ones may not have bought them, but they know they have friends, they have peers who have bought them. Very comfortable, becomes very easy to adopt them. So sneaking them into everyday use is the way to do it.
Luis, you are the next.
Very nice talk, Robin. Do you have data in Texas? How many hospitals, how many robots that were used? I don't recall to have seen many disinfection robots around during the high months of the pandemic. Do you have data on that?
You would not have seen them in a hospital. By definition, is when they're changing over the patients, right? Cleaning up the room, and you're not supposed to see the light, right? So you close the door and let it go, right? So you wouldn't see them. These are behind the scenes kind of robots. So no, we don't have data by Texas. Hospitals don't keep data that way. They, you can't even get a complete listing of how many beds are available by hospital. So it gets kind of amusing. So we don't have data on that, so sorry.
Right, thanks.
Yeah. I saw Peter raise a hand, and then Mitch next.
So just a quick question, Robin. This is a great sort of catalog of what was done, but presumably you probably have some intuition or thoughts on what wasn't done but should have been or could have been. What do you think are what was left on the table?
For me, the biggest concern coming out of all of this was the first response. And I was on this study, one of the National Academy studies about this. And the first response is, oh, we should build lots of robots now and put them in a locker. And when the next pandemic, we'll just unlock the locker, send them out, and we'll have everything. And it's like, yeah, because that's worked so well with the nuclear industry in the past. And, 10 years later, nobody even knows how to turn it on, right? And how many have a 7-year-old cell phone? Anyone? You are an unusual person. Good for you. Not the way to bet. All right. So these are all software. They're constantly upgrading. There's always that. So just try that. It's not going to be the things you use every day are the things you use during the pandemic. All the ones we were showing that got immediately adopted were already in use, already existed. They were heritage. 73% of the robots were heritage, meaning they were already being used standard for there. Very few of the engineering that you were doing is like, oh, we've got this turtle bot, let's put a tray on it. That's not exactly a high risk modification. So we want to, my fear is that we're either going to try to cache things and miss that and not try to get things into everyday use, or we're going to say, well, what we need to do is innovate, because these weren't actually used. There were only 2 robots that actually did it. You know, like you want a robot to do a nose swab and you want to do contact. And in those cases, those robots were already being done as part of research with a hospital. And even then, I'm pretty clear, putting my head in a vise and having a robot swab my nose versus the little telepresence robot, maybe not Spot with an iPad, which is just freaking creepy, right? Come in, nurse talks to me, tells me, pick up the, yes, you're holding the swab the right way, put it in your, no, I'm counting to 15, keep it in there, doctor, no, in there, you know, and turn around, do the other one, is so much more humane than, I'll hold you down, put stuff in your nose. Yeah, and don't worry, it won't go back to your brain. Yeah,
Hey,
and that's gonna work.
Hey, Robin, this is related to Peter's question. The large numbers and the trends are very interesting, but I'm wondering if there were any one-offs or underappreciated or emergent applications you saw in the single off items that we should be aware of that has a lot of potential.
I think the biggest missed potential, and now I'm coming back to, there's clearly a latency in my responses here on answering Peter's question. The missed opportunity was really to do the laboratory automation. One of the biggest initial problems with testing is that you had to have technicians test. You both had to have facilities, and then you had to have technicians. And then, okay, that doesn't sound hire people. Well, except you have to have them certified by the FDA. And then so you start getting this huge back trail of things, and so you can't rapidly absorb. So why can't you automate the laboratory analysis? And even better, why can't we give the doctors, this is what they asked for in Ebola, a laboratory automation in a box? So as you take the sample, you know, the cart that the phlebotomist takes around, you know, that cart now has a little, at least shove it in there and it starts doing a little something. Not like TEROS, but you know, something that actually works, right? But I mean, how hard, those were things that were doable, feasible, instead of like, oh, we're gonna take the sample and then we're going to drive it 30 miles across town. You know, so I think that was the one that, and with the certification of the individuals is really tough. So I think that was a big one.
Okay, I think, yeah, the last question, please.
All right, so like quick question. So do you have any insights on how the cost of these robots affected the applications and the countries they were deployed in?
Cost was certainly a factor. In the case of the cloning, the most common excuse was we can't afford it. Not excuse, I mean, I'm sure it was true. They couldn't afford it. The other thing, all the drones that were doing the nasty violations of privacy and yelling at people, those cost about, $1,000 to at most $2,000. So those are really cheap and easy to use, and we're sure that explains why they got used so much. There was no downside. They were cheap, they were easy, you had them to do it. If something bad happened, you only, you know, you're still in petty cash for most agencies. And so that probably played a role in the pervasiveness of it. So, yeah. Well, we're out of time.
Wonderful.
Here, so.
I saw still some hands up, but we are running out of time. So please catch up with Robin in the coffee sessions if you're interested. And so let's thank Robin again for the wonderful talk. All right, so I'm going to hand over to Joydeep to introduce Mary.
All right, it's my great pleasure to introduce Mary Hayhoe. Mary Hayhoe is a professor in the Center for Perceptual Systems at the University of Texas, Austin. Sorry, is there an issue? No, okay. Mary's research is in developing virtual environments and experimental paradigms for the investigation of natural visually guided behavior. And this is a fascinating area to me because I'm personally involved in research which approaches vision from the other end, which talks about like, how can we build up algorithms? And Mary's been working on like, let's understand humans who know how to do this and understand how they do this. So Mary has served on the board of directors of Vision Sciences Society from 2011 to 2016 and was president in 2015 and was awarded the David R. Teller Award in 2017 for her contributions to vision research. So I'm excited to hear about
what insights Mary can shed and what we can learn from this for robots. So with that, I hand over to her.
Thank you. Okay. Well, I'd like to echo the sentiment that it's really great to actually see real people again. So this is my first outing, and let me get rid of this. It's okay. So I'm going to talk about something completely different, which is human behavior, but with a bit of a difference. So most of the work, sadly, in understanding human vision is lots of great work, but it's the structure of the experiments just don't tell you very much about how vision actually allows you to get around the world. And so you have a series of trials. You're asking one question, like, can you detect this motion signal? What's your stereo vision like? And the experimenter is telling you what to do. But in ordinary behavior, it's evolving in time. You're making the decisions about what to do. You're actively selecting information from the environment, and nobody's telling you what that information should be or what you need. And so one of the things I like about this is that this is, you know, we want to know, okay, how do you build a human to do these things? And so this is very similar to the problem in robotics. How do you build a robot to do these things? So first of all, we just need to know what people do. And this is John Mathis walking across the road, and he's wearing an eye tracker. There's a camera on the head. That little blue cross is where he's looking. And so you can see your eyes are very busy. And we're not really aware that we're so actively getting different kinds of information. And so here it's slow-mo, and you see he looks at the curb. He looks at the girls because he wants to walk around them. He wants looking where he's going, the pedestrians, et cetera, et cetera. So the way you can think of that, this is, you've got this sequence of decisions. And so what's controlling where I go now? So you look at the right place. So how did you see the curve? You managed to look at the curve. You look at the pedestrians who might bump into you. And so we're making the right decisions at the right time. And how is all this working? Just before I go on, I'd just like to share some terminology. So these very rapid eye movements are saccadic eye movements, are high velocity movements. You're not getting any information because of image blur. Then the information you're collecting is during these periods we call fixations, which are a couple hundred milliseconds. And so that's when vision is happening, but then you're going on to the next thing. All right, and so to understand vision in the context of action, we need to know what information is needed for behavior, different kinds of behavior, and how is this information used to make a decision of where to walk or where to look. Now, this is just to say that in the last, I don't know, 15, 20 years or so, people in human motor control have adopted this conceptualization of the problem of using statistical decision theory. It's just a convenient framework, even if it's not complete. But the idea being, of course, you want to evaluate the world state in order to make a decision. In order to do that, you need to get sensory data, and then you've also got your priors about what's out there in the world. And you need to take into account the costs and benefits of that action. And so I'm going to be talking about three of these things, in particular, the collecting the sensory data, the importance of memory, and also perhaps most important, it's the cost function, how this is sculpting every tiny little decision you make when you're crossing the road. All right, and so I just want to make sort of back into a little bit about the brain and how this makes the cost functions incredibly important to think about. And so what you have here is my cursor there. Okay. So here's the motor cortex and premotor cortex. And so you have this loop through the basal ganglia, this a subcortical set of nuclei. And the basal ganglia is implicated in the choice of the action. And that happens because it's regulated by these dopaminergic reward circuits. And you also get this influence from this prefrontal cortex also on the motor cortical areas. And so every region in the circuits that control saccadic eye movements are influenced by these reward circuits. So it's a terrifically important modulator of the actions that we choose. So we did something just kind of simple. We measured walking outdoors. In ordinary terrains, we had a range of terrain difficulty. We instrumented the body with these IMUs. We have a binocular eye tracker, and you have to block the infrared, which is a bit of a pain. But eventually we got to do that. So first of all, what do we have here? On the right, you've got the view from the head-mounted camera. The black cross here shows you where you're looking. And so you're hopping along and very niftily getting information about where a good place to put your foot is. And you've got the eye and head signal down the bottom. And over on the left here, you've got the integrated eye signal and the body markers, and those little blue and red dots are where the feet will be going in the future. This little vector here is gaze on the ground. And we can, because we know where the eye is looking, we can align the images to the central fovea on the retina. And so we can actually use this to know actually what is the input to the visual system at this moment. All right, so that's nice. And so just a very crude overview of what's happening first and why these sort of various factors are involved that I was talking about. And so if you're walking along pavement here, this is like the angle of gaze. So when you're walking on pavement, you're just looking in the distance where you're going. And so mostly you're looking pretty horizontal, but you only have to change the ground a little bit and make it just a dirt path. And suddenly you're spending a little more time looking at the ground. And then as the terrain gets more difficult, you're walking like this, right? Looking at the ground all the time. And so this is perfectly sensible, but in terms of understanding what's going on, you see the task goals are changing as the terrain gets more complex. This changes the gaze distribution, this changes the retinal input and the information that you're getting. So we need to know where you're looking. So again, just a little overview of this. If you're on a flat ground plane, you just need your prior. How do I walk? The ground is flat. You can just assume you don't need to bother programming individual steps. And your locomotion is controlled in these cases by low-level pattern generators in the spinal cord or brainstem. As the terrain gets more complex, now you've got to worry about getting that information. And so you're going to use gaze to get the sensory data, more complex sensory data. And so in this case, now you need that cortical modulation of these low-level locomotor control systems. And importantly, the cost function changes because if it's rocky, one is you need to find stable footholds, but it's also more difficult to work and it's costing you more energy. And people are really lazy. They always like the lowest energy solution. So, well, not always, but it seems to be a very important factor in even simple little situations like this. And so these decision circuits modulated by the dopaminergic reward machinery become quite important. And so this is just somebody walking in Shoal Creek. That was actually, you can see him, this was some of our early observations. And so he's actually wearing a welder's helmet to block out the infrared. which messes up the eye tracker. But however, so you can see, so what does he need to do? He wants to get to his goal, and you want to get there usually pretty quickly and as straight as you can. You've got to find foothold locations compatible with energetically conservative policies. You don't want to fall over, but you've got to do all of this and make these decisions within the time frame of a single step, which is about 400 milliseconds. And so once you start thinking about it, you think, wow, can we do that? And how does it all happen? We're completely unaware of it. So what do we know about locomotion? And a lot of the work historically has not even considered the visual system. It's on treadmills or flat surfaces. And so the bottom line is we don't know a whole lot about the visual motor control loop, these very complicated visual motor control loops. Now, previously, I showed you the integration of the eye and the body data, but that's not good enough if we want to know what we'd like to know is what is determining the choice of a path. And so to do that, you really need to have a representation of the terrain. And so what we do is use photogrammetry to recover the 3D structure using the sequence of head camera images. And this also allows us, because the IMUs are kind of drifty, by being able to link the terrain to the body, we can get much better estimates of where the feet are, and also we can get better estimates of where gaze is, because now we don't have these parallax errors. All right, and so this is what we get. This is our kind of data. Our little guy walking along, the pink spots are where his feet will go, and so these little blue cookie crumbs those are where his eye goes. And you see, we can analyze this data, and they actually look very, the gaze is distributed very pretty tightly around the actual foothold locations. But you can see also looking off, you have to make these decisions about changing direction. And so some of those fixations are distributed laterally as well. So what's going on? Can we actually predict where somebody will walk in a situation like this? And so first of all, we have to say, is there something to predict? We better be careful here. And so do people choose similar paths? And so here you've got two observers on the left there, and the blue is one person, the red is another person, and then they walk this route 3 times. And so you can see that in some cases, you can see, there we go. Up here, all trials and all observers are converging. This seems to be a good spot for walking. And you might do the same thing twice, but here different observers choose this path. There's something good about that. So a little more divergence over here. So there's clearly something to predict, although there's also a number of perfectly viable paths. All right. So what we want to know is, we want to know, why did you choose this path? And so what we did is we take a given footstep, and what's the path you took 5 steps ahead? And what are random paths? So we want to generate some random paths, but they have to be plausible. So if you're here, you're limited by your leg length, how far you can step, right? And so there's a distribution of step lengths, there's a distribution of changes in direction. And then also you can't step so we generated a set of plausible random paths. And then what we did was we calculated for this 5-step sequence, you can calculate how many changes in height there are. So that the mean changes ups and downs across there. And so that's what we got plotted here. These histograms are the mean slope. And so you can see the mean slopes, the this pink, this disgusting pink plot here. Carl chose it for some reason. However, you clearly you choose the paths that involve less up and down, and the random, the distribution of the random paths. So there's a fair bit of overlap. So again, suggesting that walk is a kind of, there's some flexibility. Some paths are perfectly fine and equivalent. So you're not really very tightly locked into a particular path. All right, so what is this? This is what we did here was to look a little bit at the choice of more circuitous paths. And so for a 5-step sequence, you take, okay, the shortest, if I walk straight, what would be the height changes? And then if you choose not to do that, you want to measure how long the path is going to be that you chose instead. So you chose this instead of going straight. And so what we've got here, this is just one observer. So as the mean slope for a straight path increases, then you're more and more likely to choose a circuitous path. And so these don't show up very, the little blue spots, they're not too bad. So it's actually a pretty tight correlation. So it's kind of, again, neat that you're trading off the cost of these height changes with the cost of longer paths. And this was not a fluke for one subject. This actually happens for all 9 of the subjects. And and interestingly, I'm not showing you the data, but interestingly, this depends on your leg length. So people find nice operating points for their body. Again, it's kind of surprising that we're making these little trade-offs on this very short time scale. All right. So what we're talking about, so when you reconstruct the terrains, what we were using in the previous analyses was the actual mesh representation of the terrain, but we don't know for sure that this is what the subjects have access to. So what we took was the subject's perspective depth image, and we use this to train a CNN. So got trained to recognize the real footholds, and so then we took another section of the path and tried to predict the footholds in that other section. And it doesn't do too badly. So the green circles are the actual footholds, and the heat maps are the sort of predicted footholds from the CNN. And so if you then say, how good is this? Then these are our 9 observers over here. This is this measure of area on the curve, the metric for area on the curve, to measure how good you're doing, well above chance, usually between 0.7 and 0.8, which is not too bad. And so this tells us that these depth features are actually important predictors of foothold selection. So we don't know if there are other things at this point, but this is about as far as we've got. So just to summarize, the factors that are influencing your path choice is you really like to avoid these big height changes. That's a little different from, there are other things that control your path, like a really big rock. You will avoid that, and often looks in the distance, you're probably saying, this is not a good way to go because it's a giant rock there. But on this sort of more local scale, you avoid these energetically costly ups and downs. Minimizing these height changes is also going to influence stability. And so it's a little bit hard for us to know at this point. We can't disentangle the stability constraint with the energetic cost constraint. And there's also flexibility in that. So, but the nice thing is that people also neatly trading off the cost of these height changes with the cost of longer paths. And that's presumably one of the things that is guiding them when they change their, as you saw them weaving around a little bit, presumably this is what they're doing. The other point I'd kind of like to draw your attention to, and I didn't really show this very clearly in the talk, but the path choices that depend on the slopes over about 5 steps. So when you're walking, you're not just you're getting visual information. You're not just planning the next step. You're planning pretty much the next 5 steps. So the I don't know how we do that. This seems it would be nice to be able to model that, and so that simplistic diagram I showed you doesn't. I was sort of again, I tried to just represent the fact that you've got 5 steps planned ahead, and you're also predicting what's going to be happening. And so to really have a better understanding of this, we need to understand this sort of kind of planning window of about 5 steps. I don't think it's much longer than 5 steps, because if you look at where the fixations are, they seem to peter out at about 5 steps. And then also that's at the point when you look into the far distance. All right. So these are the people involved in this. John Mathis, who started it all and is now at Northeastern University. Kate Barnon is at Indiana University. She was a graduate student here. Current graduate student Dan, and Carl Mueller has just left to look at satellite images and things like that. So thank you.
All right, questions? Luis?
I'm coming.
Do you have studies on the kind of mean velocities?
Yeah. Yeah.
That would be also very interesting. And also,
yeah.
Studies for much greater as well on age, person, depending on the population you choose, right? But velocity probably is the key as well.
We haven't looked at the individual differences in speed, but yes, basically, the first thing you do is slow down. And so, and that's where I think it would be nice to know if you actually kind of categorize the terrain and sort of general characteristics of terrain to set some parameters like speed, gate speed. Yeah, that's I think that's how you preserve avoid the energetic costs. Is just slow down, and that probably gives you the stability, because you have longer to get the visual information you need. You can find the good footsteps in time, and yeah, slowing down is something we do all the time. Also, even when we start thinking while walking, you'll slow down. So yeah, that's a big one. I don't know about individuals, but yeah, it would be interesting. Again, this probably could be easily adapted to aging people and things like that.
My name is Swami Gopal Swami from Texas A&M. I'm working on autonomous vehicles. I found your this presentation is fascinating. Thanks very much for that. So one of the questions that came to my mind is when you're walking, the gaze seems to be looking at 2 different types of things, right? Based on the angle. You did have a chart on the percentage of time that they may spend in one versus the other, depending on the terrain. But do you also have a sense for what kind of mental model they may have on based on the 2 different gazes? So one a more detailed terrain model mentally, and then one an environment model that could in turn perhaps drive their decision-making process.
Yeah, totally. I think that's a lovely question. It's not something we've got to in any detail, but I think that the longer, the looks in the distance, to say, yes, well, this is a good direction for me to head. And so that might sort of set your criterion for you don't want to deviate from that direction. So it might constrain you in that way. But yeah, I think there's a whole lot of really nice questions there. And definitely those looks are for different purposes. And yeah, initially we were trying to think of, I wonder when you time those looks in the distance at a certain phase in the gate cycle, or we haven't looked at any of those things that would be nice to do. Yeah.
I don't know if you can. So I have a bit of a tangential question. I'm a student here at UT, and we use virtual reality for a lot of our experiments. Perceptual experiments.
One of the things that we have been working on is a somewhat different question, which is, so when during the gate cycle, you generate these complex motion patterns on the retina. And we think that that's probably regulating your posture. And so we've been looking at that particular thing because historically, again, in the vision field, people have taken these flow patterns on the retina and said, oh, you use that to guide where you're heading. And, so we were just testing that. No, we actually think it's much more local. And if you get a sort of a biased set of motion vectors, then you're falling or something like that. And so I think there are lots of really interesting things to do, and we haven't actually got around to even planning them at this point. But yeah, I think it's
then Mitch.
Hi, I'm up here.
Hi.
One from him. I really enjoyed your talk, and I think I took your class when I was a grad student here. But then one of the things that you mentioned, the 5-step planning, relates, I think, to we had to do a similar experiment where we were walking on level ground, and we were not interested in gaze, but we level ground transitions to stairs, and how far in advance people alter their coordination and muscle activity and things like that. And we actually showed if you're counting steps, so 2 strides of each side, each leg, that even as far away as that, so 4 steps away, people like downregulate muscle activity or upregulate muscle activity, depending on which foot is going to be the first that touches the stairs. So kind of really cool stuff, but not at all interested in gaze, but it seems so relevant.
Consistent,
Yeah.
About this.
And then I guess my question would be that how do you square the concept of like central pattern generators, right? Where people think that most of the circuitry for locomotion is like within the spinal cord versus in the brain, the brain directly driving locomotion. So some people sort of think that people are unstable when the brain kind of gets in the way, right? When you have to make a conscious decision as opposed to just being sort of an autopilot on flat ground. Have you studied anything to do with how the brain activity changes with the different severities of the terrain?
No, that requires somebody with skills in physiology. But I think the trouble is really you sort of limited, like none of the animal work. You just can't record them when they're walking, and so it's just human work, and the precision of the spatial precision is limited too. So I think people don't know as much about this as they should. But I think that I don't think the cortical control is. I think everything is cortically controlled. And so you've got the loop through the cerebellum, and so the signal that's coming down from motor cortex is already it's had a lot of fine tuning from the cerebellum and things like that. So I think I don't see cortical control as a problem. Everything has to be cortically controlled. It's just like I think so. But I mean, interestingly, there are other things. This is a little bit of a tangent, but the vestibular ocular reflex, which stabilizes, it actually, the gain goes up when you're walking. So somehow or other, the spinal cord is saying, hey, you're walking, better amp up that gain so you get a good visual signal, right? So it seems to me that they have to be able to talk to each other seamlessly.
Thank you. One final question and then we'll break.
This is great. This is the kind of data set that is always going to lead to 1,000 more questions with everything you do. And so it could easily devolve into, did you consider X, Y, or Z? But I'm going to ask you about two anyway. One is, there was the creek, which seemed to kind of predefine a general path that they would take. And I'm wondering if it was an open rock field, if you had the idea that maybe people would have looked up more, even in a rocky area, because of more freedom on what path they could take, and if there was a restriction there. That was number one. And the second one is, I know that when I climb on rocks like that, I spend a lot of time trying to guess whether that rock is going to be stable or sink or not. And I'm wondering if there was any way that you were able to figure out to possibly include that in the prediction model.
The first one is, I think people just, what's the quickest way for me to get where I'm going? And so as long as you have a goal, we all want to take a straight path. That's our first, and I think that's a real constraint on what you do. In terms of the stability, I kind of think we're a little bit kind of gazelle-like, and so that might be something where you can leave it to, either learn, maybe some of the reflex circuits to sort of, so you step on this, little bubbles a little bit, and so you quickly change your weight. So there's a huge number of interesting things about locomotion that we're just not even touching on here. And I'm actually, I used to think, locomotion, that's really boring, And but when John came in, I said, maybe it's interesting. But I'm not actually that much of an expert on locomotion. I'm just, it's a huge field, and so I'm really just focusing on the visual control, and in this case.
Well, thanks so much, Mary. This is a fascinating talk, and I'm sure I'm going to ask on behalf of all of the roboticists who are dying to ask you. We would love to get hold of some of this data to actually teach our robots, so we should chat more.
Oh, totally. I think that would be fabulous. Yeah. No, I'm really excited at the possibility of making these data sets available.
Yes, and I'm sure there'll be lots more questions. Let's take it over the coffee break. We're going to break for a coffee break. Let's thank Mary.
Thank you.
And we're going to
Okay, maybe it's on this side. Try that.
Okay, so now.
Texas A&M University.
Thank you. It's a great pleasure to be here to share some of the research we have at Texas A&M. My name is Deso. I'm a, let me see if I can unblock it. All right, so today I'm gonna, talking about the autonomous vehicle research we done from perception perspective, mostly from the sensor fusion perspective. I will take us back 20 years when I was still just a grad student at UC Berkeley, when we a student group decided to participate double grand challenge in 2004. We, out of innocence, so we trying to use the motorcycle as the platform because we believe it can go off-road and deal with what is being required. Because double grand challenge, just give you a little background. At the time was U.S. was involved in Iraq War and the convoy truck was hit. So the DoD trying to see if anyone come up with solution to make the vehicle drive by itself to cross the desert terrain. So this is actually the competition course of 2005. You have to drive a vehicle over 155 miles. So a group of us, just no faculty involvement, was trying to start a team using the motorcycle. So at the beginning, nobody believed this is doable. So Berkeley does not allow us to use any Berkeley logo or name on this. So we only call us Blue Team because the color. So we were able to pull it off to get the vehicle running and balancing itself and cross some different type of terrains. Of course, perception-wise, we actually have very minimum design of perception. Now you think about this is a 2004, 2005. The computation power is no more than today's cell phone. We only use, there's no 3D LiDAR at the time, okay? And we only have one onboard camera, the GPS, and a fiber optic gyro MU on board. That's all we have for navigation purpose that get us started for sensor fusion project. So in fact, that project ended in 2006, actually, I would say, when DARPA moved into its urban challenge. We did not participate at that stage because this is explicit requirements that you had to have 4 wheels. So at the same time, I already moved to the A&M to start my faculty life. So my teammates at Berkeley founded a company called Berkeley 510 System. The site is secretly acquired by Google. They built 2 cars, which is shown here, the Google Street View and the Waymo vehicle later on. I'm very proud of our teammates at the time. But at A&M, I actually start thinking from a minimalist approach, how many sensors, what can you do about it to get a navigation functionality? Can you do this on small robots? One robot we think about is, can we do this for 4-wheel robot without steering mechanism? This is a skid-steered robot platform, independent 4-wheel drive, no steering mechanism, but we have customized the 1 kilohertz control frequency. We're trying to see if we can get this vehicle running off-road with high agility and to do 20 miles per hour. Can we do this? Well, of course, the challenging part is kinematic modeling of this thing is pretty difficult. In fact, you have to model the 5 body differently, but the sensor perception side is also very important because you have to know the vehicle status because you cannot read your steering angle. There's no such a thing exists. So we have to use 4-wheel encoders. We monitor the speed differential between these four wheels to estimate the skip on each wheel. In fact, at the end, not only we can control this vehicle, we fuse the multiple sensor from IMU, 4-wheel encoder, all this minimum sensor suite. Well, when we can do trajectory following, we can also determine what kind of terrain we are. Are we on a high friction, carbon-like terrain, or it's a low friction, sandy surface? That we can tell that. We can also control our control parameter based on this, so that the minimum sensor fusion. So that is actually kind of become one of the signatures. What is a minimum sensor you need with a minimum computation power to do things you want to do in the navigation side? So fast forward to 2015, well, my PhD student and I was thinking about the problem that we're working on is Well, you cannot always rely on GPS signal when you drive in a city. What if you have whiteout snow? What if you have severe thunderstorms, decrease your visibility to 0, but you still need a location, right? How do you find out where you are? And the problem like this is not unique in Texas. So the thing we were thinking, most time we know where we are citywide. I know I'm in Austin. I'm not in San Antonio. That's quite clear, right? So that's a prior we can use. Another thing we already have is every vehicle nowadays have a digital compass. Know your headings. You see that in your vehicle. And plus it has a IMU built-in. All the modern vehicles actually all have IMU built-in. You probably don't have access to it, but it does have one. So with 3 information, I tell you that's enough to find out where you are if you just drive on the road for a few seconds. So how we do this? If simply you can monitor your heading change as you drive on the street, you can discretize that into a query data structure. You query your map, and you can find where you are. As long as you don't live in a place like Manhattan area, you can find where you are in 5 to 6 turns using our algorithms. So we call that is map-based localization is a traditional problem. It's also does not depend on any exterior sensor, or we call it proprioceptive sensing, because only just like human data reckoning, you don't need to rely on outside sensors. So no matter how bad the weather is, you can find where you are. So that's also a very minimal approach of sensor fusion. So all these 3 kind of reflect to the principle of the research we've been doing. We're using all kinds of sensors. So we'll just here, I just want to list all these 3 pieces of work we've done so far. At the last, I want to mention our recent effort. We are leading Texas A&M team. Actually, Professor Gopal Swami is also here. He's also a faculty advisor on this team. It's our auto drive competition team. What happening? This is the competition organized by General Motors and Society of Automotive Engineers called Auto Drive Challenge. Auto Drive Challenge 1, the first competition happened from 2017 to 2021. It's a 4-year competition. Every year, you bring your autonomous vehicle to a same competition ground to compete with other universities. There are like 80 universities applying for this. 80 universities was picked by General Motors. Each of us get a donated vehicle. And also, we are responsible to design perception system and navigation algorithms. On top of that, then we go to the test ground. In this case, it's a year 2 test ground. It's the MCT in the University of Michigan. 8 of us from US and Canada, 80 universities, competed here for 1 week for different things. And so, of course, all the previous lessons we learned help us to build this navigation algorithm together. But one unique challenge we're facing, as you may know, in year 2, we have a group photo on site. And we did a lot of tests and development on the physical vehicle. But what happened is we don't really have year 3, because year 3 is 2020. Everybody knows what happened in 2020. We're not allowed to touch our vehicle. And in that year, we're kind of in a unsettling status. So how are we going to do autonomous vehicle research without touching the vehicle? And then that part, especially for perception, we need the real data, not just open data set, because we know we need the data for specific time, speaker location, and all the sets that may not be covered by the open data set. So we were thinking, what can we do to address this problem? Of course, we all know we have to do things over Zoom. This is our group photo at a time. We can only crop copying the Zoom photo together. And in fact, what we tried this year, I think is quite interesting, is we also thank for the software from the Masterworks. Is one of the sponsors in the process, right before the pandemic, they start developing a software, new features for MATLAB Simulink that can be linked to 2 things. One is an Unreal engine, do the real thing rendering. The other is directly linked to the raw stacks. So what happens is all the stacks on the software on the vehicle are raw stacks, can be tested in closed loop in the simulated environment. For the first time, we can do that from perception all the way to vehicle control, the full loops. In fact, we only had 2 weeks of vehicle time in year 4 to adjust parameters to fit the real vehicle. And we did use that platform and testing What happens is, I give you an example here. This vehicle is approaching a traffic light, and it's able to detect it and say, hey, this is nothing. When anybody learned in deep learning class would know how to do this. Yes, that's no trivial. But what the underlying signal behind is, we did a for loop. This similar environment generates synthetic perception data streams. That including synthetic camera image, I can choose different lighting conditions. I can change that. We also generate lighter data using the particular brand of velodyne model you are using, how many lines you want to generate. You can also generate the minimal wave radar. So we can use that as well if your algorithm uses it. Actually, our algorithm uses that as well. So you might say, hey, you can use this train to mix with real data to train your algorithms. But what's the really implication behind this is, this enables us to test on the scenarios we'll never be able to do before, like create accidents, create abnormalities. Because one of the problems we had in the research is, we always had the normal driving condition. We don't have exceptions, and this allows us to do that. So I'm going to stop here, but at the end, we were able to win the championship of this 4-year competition. So we're very proud of our team. So that's kind of close my talk today. All right, thank you.
Thank you so much. Our next speaker is Professor Vaibhav Unhelkar from Rice. See you. Thank you. Any questions? Got a little bit of time. Okay, great. Thank you so much. Awesome. All right. Our next speaker is an assistant professor of computer engineering at UT Awesome, Professor Sandeep Chunchali.
Oh,
great.
I think
Okay.
this should be fine too.
You can use that. If that works for you, you can, or whichever one you prefer.
Okay. So thanks for the invite to be here. My name is Sandeep. I'm a new assistant professor in the ECE department at UT. And my work is broadly on networked and cloud robotics. So in other words, how can resource-constrained robots, such as low-power drones, augment their real-time computer vision capabilities, as well as distributed learning capabilities using 5G wireless networks? So today we're starting to see fleets of networked robots, ranging from low-powered drones to this Amazon Kiva manufacturing robot in orange. And we're starting to place very high hopes and demands on these robots, right? So ideally, they should be cheap. At the same time, they should also be compute, memory, and power efficient. But finally, they should also be highly autonomous and resilient in the physical world. But this is somewhat at odds with the way we're building ML systems today. So we're building computer vision and natural language processing models with millions to billions of parameters. They often require power-hungry GPUs to run for real-time inference, but they also require quite a lot of labeled human data and cloud computing time to actually train these models. So in other words, they're highly accurate, but at the same time, they're very compute, power, and data hungry. So this trend is actually starting to become very untenable for the most resource-constrained robots. So the key question that motivates my research is how do we actually scale? So can we actually build swarms that are compute, memory, and power efficient, but also gracefully augment their computation using offboard computation? So if you return to this question of how to scale robots, if you look at the software industry, so software applications have scaled very well using cloud or centralized computing resources. So a natural question to ask is whether robots can also benefit. So one benefit could be if you have a low-powered drone and you're uncertain, you can augment your perception in real time. So in a 5G wireless network, you can offload perception to maybe a nearby cell tower that has a better GPU. But these benefits actually help robots that are not necessarily computer power constrained. So Intel estimates that a self-driving car will measure about 4 terabytes of rich sensory data in an hour and a half. So you can continually learn from this rich data stream by statistically sampling rare or out-of-distribution data. So despite the benefits of the cloud, there are actually understated costs that we typically have today in robotics, right? So our wireless links have intermittent connectivity. Their throughput and latency varies across space and time, but also their economic costs. How much do I store? How much do I label? How much am I willing to spend on training? But there's also real-time delay. there's delay from communication as well as invoking larger models at a centralized server. So given these benefits, but also these end-to-end systems costs, most of my research is on building robot cloud collaboration algorithms that are decision theoretic and they're somewhat economic in nature. So robots should estimate the marginal accuracy gain of using network computation and gracefully trade that off with systems costs. So we work on fleet learning, dynamically selecting between local and cloud computation, and also how to represent data. So for those of you on Zoom today, we're using standard video protocols. So every pixel essentially matters the same. But a lot of the video in the future might actually directly be consumed by mapping models or deep neural networks. So we have an opportunity to send much less over the air and still get the same sensing task accuracy. So I'll just preview some of the work we've been doing. So collaborative fleet learning. So we've tested this on gigabytes to terabytes of data, some of my commute data as a grad student every day at Stanford, but also with collaborators in Cornell. So an autonomous vehicle might see a well-understood freeway scene or a dynamic construction site or a rare event, like a self-driving car being tested on the road. So this isn't a stock image. This is actually from my dash cam. So today you just upload, store, and label all this data, typically, and it's very expensive to do so. But the benefit is you can quantize and compress these neural networks to run on low-power devices. So this USB stick here has about 8 megabytes of memory. It's a low-power edge tensor processing unit, and it consumes about 3 watts of power, whereas a small cloud GPU would be 200 watts. So some of my work is actually building intelligent sampling algorithms that essentially act as data-driven filters. So they learn to reject these well-understood scenes and just harvest interesting training examples to balance accuracy benefits, but also these end-to-end systems costs. And some of our work is looking at real-time perception. So let's say you can crowdsource interesting data from a fleet. You can train large models optimized for the cloud, or small models that can run on your microcontroller. So we're building selection algorithms in gray that are essentially Markov decision processes. So given a sequence of video and past history of a robot, can I decide at every time point whether I should use a fast responsive local compute model on the left, or only if I'm highly uncertain, should I use a larger model that's slower but can localize far off objects? So we actually solve this MDP approximately as an RL agent, and we deploy it with minimal overhead on GPUs. So some of our recent work is now looking at the representation of this data that we offload for video, both for learning and real-time perception. So this is a recent paper published in RSS. So let's say your robot sees a sensory data X, you encode to Z. Typically, you would send it over a wireless link and decode to X hat, assuming that the fundamental consumer is a human. So every pixel matters the same. That's how information theory and rate distortion theory works today. But if the consumer is a deep network, if you look at the sensitivity of the ultimate task accuracy with respect to pixel distortions, you can use that as feedback to co-design a neural compression scheme. So we actually tested this on low power accelerators. You can see some of the plots on the right. So the y-axis is task loss, so lower is better. And the x-axis is how much data I share. So red are standard video codecs, which take more data but get lower accuracy, whereas our schemes are in blue and orange. So they're more data efficient, but do not sacrifice on accuracy. So some of our recent work is actually not quite in robotics, but pushing this idea of learning representations to network control systems. So this is a paper in Europe this year. It's actually inspired by some work I did in industry at a startup that's now part of VMware. So let's take AT&T in Austin. They cell congestion forecasts are gigabytes of data in real time per day. So let's say AT&T gets a high volume time series S, and they want to share this cell congestion forecast to Uber, so maybe Uber can better route its cars across the city. So I would take this large time series S, I would encode it using learnable parameters theta E, and send it across the data boundary that limits how much data I share, but also privacy regulations. But then the ultimate consumer is a control authority, say Uber. So today I would just decode to minimize mean forecasting error. So every feature of this time series roughly matters the same. But if your ultimate consumer is model-based control, so So this is a differentiable model predictive controller about how to route your cars. Then the ultimate objective is your task cost. So if you take the gradient of the cost with respect to the input, you can guide your lossy compression schemes, but also prioritize which features matter the most and how do I actually price them. So we've actually looked at this same framework and how we can synthesize adversarial scenarios for perception in robotics. So we've actually used this kind of framework, sensitivity analysis to drones, for example. So I'll just finish up by some applications. So in a future smart city, you might have Teslas or autonomous vehicles that generate huge amounts of driving logs. And you might have some delay tolerance about when you send them across the city. So ideally, if you have a forecast of cell demand, you should update your maps only when it doesn't degrade real-time traffic, such as voice and Zoom. So we're actually using these model predictive control techniques to schedule traffic. So this is some data that we did with this network operator in Australia called Telstra. So with that, I'd like to conclude. So there's a lot of buzz about representation learning in robotics, but turns out it can also help us decide how to communicate between robots and network servers. Thanks.
Thank you so much. We've got time for one question. If not, all good. Okay. Thank you so much. Okay. Our next speaker, you were all set with the mic? Right? Yep. Okay. Our next speaker is a professor of mechanical engineering from Rice University, Professor Marcy O'Malley.
May I hide this? Right. Well, thank you again to the organizers. This has been great. Good to see everybody in 4 dimensions, right? Not just little boxes. No? There we go. All right, so most of you who are aware of my work know about my work because of my collaborations with Ashish, which are sadly on a small hiatus, but we're gonna get back together. So I'm not gonna talk about this today, but I did wanna make you aware, if you're interested, we are still actively working in the area of exoskeletal robots for upper limb rehabilitation. We design robotic devices, we develop the control algorithms, we also do human intent detection, and then all the way to sort of early stage clinical translation in impairments like spinal cord injury and stroke. What you may not know is like the other half of my lab, which is haptics. So I'm a haptics person. I started in the field of haptics over 20 years ago. And I'm just really fascinated by the sense of touch, right? I think touch is really the most fascinating sense because unlike vision or audition, it's bidirectional. No matter how long you look at me, you can't make me speak faster. No matter how long you listen to me, you can't make me slow down and speak more clearly. Right? You have no ability to affect through the sense of vision or the sense of hearing. But through touch, you're manipulating the environment. You're exploring and inducing the receptors in your skin to have this neural response that you would then interpret as textures, as squishiness, as temperature. And this really is a great playground for a mechanical engineer to think about how we can recreate that sense of touch for human users. So, and what's really interesting about touch is it's distributed over our whole body, right? Skin is the largest sensory organ that we have. And within the skin are a huge range of different types of sensors. So we're doing sensor fusion every day. The ones that are most interesting to me are the Meissner corpuscles. We use these to sense slip or to control our grasp. The Merkel disc receptors, this helps us sense pressure, form, texture, and edges. Pacinian corpuscles help us sense vibration and roughness, and the Ruffini endings are the sensors in our skin that tell us about lateral forces or shear of the skin across the surface of the body. So we have all of these different kinds of touch receptors. So if we want to recreate the sense of touch for humans, we need to think about what are the appropriate devices and which are the right cues that we want to convey back to them. So now taking this to the area that I've been working in the past few years, this is wearable robotics, wearable haptic devices for communication between humans, robots, and agents.
So maybe you've got a Roomba at home and you really wish that you could have a real-time notification that its battery is dying or that it's stuck in a corner. Perhaps you're trying to navigate the rush hour traffic in Austin and you don't want to visually attend to your navigation system. You would like some haptic cues that tell you when your turn is coming up or if there's a slowdown in traffic. Or maybe we want to add that haptic sense to our Zoom calls so that we can communicate social touch as well. So for me, the challenge in all these applications is what is the information that we want to encode? So what's important about that status of the robot or the human interaction or the virtual environment that I want to convey back to the user among this set of different touch experiences that I can provide? And then what's the right device to do that? Again, coming at this as a mechanical engineer. So I'm going to just highlight a few of the different projects that we've been doing in the lab, from the very simple to the more complex systems. So this is one of our first forays into wearable haptics. So this is a transradial amputee. She's using an EMG controlled prosthesis. With that prosthesis, she's controlling the pose of the hand. And we're measuring the pose of the hand through an encoder in the system, and we're mapping that to a haptic rocker that's shearing the skin back and forth. So the amount of closure of the hand is mapped to a degree of skin stretch, and she's able to use that information so she doesn't have to visually attend to the pose of the robot, of the prosthesis, for every task that she's doing. The success of this was moderate. She really liked it. We weren't able to show that that haptic cue itself was useful for this task, and I think that speaks to the challenges of what is the key piece of information that we want to measure and translate back to the human operator. In this case, it's a very intuitive thing, pose to stretch, and so in some of our applications, it's a little less of a straightforward mapping. We've been working for actually a good bit of time with Houston Methodist on endovascular surgical skill training. We're interested in using haptics to provide real-time performance feedback to the surgeon. The way that training works right now in endovascular surgery is that a resident stands at a physical model or a VR simulator, and over their shoulder is an expert who is studying what they're doing. Right, so here the trainee is inserting flexible guide wire and catheter through a sheath into a plastic physical model that's anatomically inspired. They're visualizing the 3D anatomy with this real-time fluoroscopy image, and the expert is standing over their shoulder with a checklist that looks just like the same kind of feedback that you might get from the conference organizers here on a scale of 1 to 10. How great was this experience, right? So it's useful, but it's subjective. And it really depends on what are the metrics that you've chosen to assess. It also takes an expert to do this assessment. So our collaborators were really interested in finding a way to do objective assessment of skill, and then a stretch goal being, now can we provide that assessment in real time to see how it might affect performance? So I'm going to fast forward over about 3 PhDs and tell you what we're doing now. We had a really great success in showing that the kinematic measures of the tooltip movement smoothness, so the smoothness of the tip of the guide wire and the catheter, correlated to expertise. And not just enough to differentiate our graduate students from expert surgeons, but to differentiate between residents, fellows, and attending surgeons. So really fine-grained assessment of skill. So now that we can do that, we're mapping to a real-time feedback environment. So our trainees now work, we've gone from a box to a mannequin, same task. They're inserting flexible guide wires and catheters into this mannequin. We're performing navigation tasks to different targets in that anatomy. We're tracking in real time the tooltip trajectories, and from that, assessing performance in real time based on the smoothness of the tooltip movements. We then map that score to a very simple haptic cue. We're using a vibratactor worn on the arm, right? Surgery itself is really cluttered with visual feedback and auditory feedback in the OR. They wanted a haptic cue. And so it's basically very simple. 3 annoying buzzes if your movements are really jerky, 2 moderately annoying buzzes if your movements are okay, and 1 refreshing, smooth little buzz to tell you you're doing a good job. We give this feedback every 10 to 15 seconds, depending on the length of the task. We've shown in non-surgical tasks that this changes folks' strategy and how they perform tasks. They become faster without loss of accuracy with this kind of feedback about their movement smoothness. We're providing this feedback in a wearable device that's embedded with linear resonant actuators. This is open source hardware and software that you can find on our website, syntax.org, if you're interested in producing your own wearable haptic feedback devices that do vibration. All right, 2 minutes for 2 more quick projects. We had a fun project with Facebook. Now getting a little more complicated with our wearable devices and the different haptic cues that we're providing. Here we wanted to take combination multisensory haptic cues that include stretch, squeeze, and vibration, and encode phonemes, or the parts of speech. So just as you're driving home, you could get a text message, and instead of having to look at your wrist, you could feel a sequence of haptic cues that map to the phonemes in the phrase, "Can you pick up dinner?" You'd be trained on this phrase, and then you get the message and go pick up your ramen noodles and bring them home. Hi. So the challenges in this particular task were that there were two aspects to haptic communication. First, you have to reliably perceive the haptic cues, and second, you have to learn the mapping of those cues to the information. We went through a series of psychophysical evaluations to show that people could do that identification. They could feel these multisensory cues and correctly identify the components. And then we could teach them through a GUI training interface how to map those cues to the phonemes and put words together. With 100 minutes of training, they had word recall accuracy from our vocabulary of over 90%. All right, last bit, because this is cool videos. I really want to get to how we can feel objects that don't physically exist. So we're taking an approach called referred haptic feedback, providing haptic feedback on the wrist that would normally be felt at the fingertips. We want to avoid simple, low-fidelity hand controllers and complex, bulky haptic gloves and do something in the middle. So we have a device called TASB that incorporates 6 fiber tactors and a really cool brushless DC motor pulley mechanism to squeeze around the wrist. There's the squeeze. There it is in action, right? So squeezing, it's about the size of a smartwatch. And the magic is in the how we put it all together. So as you're interacting with objects in the virtual environment, we're using either the controller for hand tracking or the head-mounted display for tracking. We're giving you a small vibration cue upon contact. As you depress the button, you get a continuous squeeze cue proportional to the stiffness of the button that we want you to feel. And then we can overlay that with visual pseudo-haptics, which is showing you that your virtual hand is in a different location than your physical hand. And that mismatch we can use to play with the sense of effort that you feel that you're extending to experience the task. I'd be happy to talk about this more with you at the next break. Thanks.
Give it a minute. All right. Thank you so much. Last but not least, our final speaker is an assistant professor of mechanical engineering at UT Austin, Professor Farshid Alimbegi.
All right. Okay. All set. Hello, everyone. So I'm Farshid Alimbegi, an assistant professor in UT Austin. So I started my job in 2019. My reference is COVID, so 1 semester before COVID. So I had 2 years of challenging time during the COVID, but thanks to my students, we could do cool, basically, work that I'm going to show you. So the topic today I'm going to talk about is robotic surge engineering of spinal fixation procedures. So here's my lab. So a few months ago, we had like a fancy team video recorders from UT came to my lab, made this nice video of my lab and Dr. Ann Fay. I guess she's not here. So we are the 2 faculty doing basically surgical robotics in UT, Texas Robotics. So my lab name is Advanced Robotic Technologies for Surgery. We call it ART in short. And the goal here is that we are going to use the name surge engineering or engineering of a surgery. The meaning is that actually so far, most of the work done in robotic surgery or like from the engineering perspective is that surgeons coming to us saying, okay, here is the need, make something for us, but it's not going to work. So with surge engineering, we are going to work together along the path to make something, some technology from hardware to software that we see the need in the end and then back design it in order to have something to be useful. So with that, I want to start with this nice plot I always show it in my talks that x-axis are the important years in terms of milestones in development of different technologies in surgery. It starts with actually open surgery, so the tools that they develop to do surgery on patients. In open surgery, what happens, surgeons going in might make very large incisions. The good thing is that in this way, surgeons have direct access. They can see anatomy. It makes it very easy for them. But patients are not happy with this regard because it takes time for them to get better and then recover. So then they started to talk about minimally invasive surgery. What happened, instead of having large incisions, now they have small holes, like up to 1 centimeter, 2 to 3 holes. Instead of having a direct access for surgeons, they have small holes, tools going inside, and then surgeons trying to do surgery. In this regard, actually, surgeons are not happy because they have lost the direct access to see the anatomy and then manipulate the tissue. But from patients' perspective, they are very happy because the recovery time is much faster. So about 1990, like Intuitive Surgical came in and introduced the robot Da Vinci. You might have heard the name. So the cool thing was that the idea was that make surgeons and patients both happy, because what happens, they have a very nice console. They can sit behind, they have a 3D view, and they are doing minimally invasive surgery. So no large incisions, very nice and comfortable actually platform, all robotic. So currently there are actually a lot of surgeries performed using this device. So this is old, this is up to 2000. Now after 20 years, we have different versions of actually Intuitive Surgical Da Vinci robot, and they have another product actually in the market called Ion. Top right, you see their single port Intuitive Surgical Da Vinci robot, in which you see instead of using rigid tools, you have one port, you have a snake-like robots coming in, you have one endoscope which is flexible, so you have more dexterity to do basically the task. So the last two elements here, milestones, are basically, this is the topic of research mainly for the last 10, 15 years, is developing tools and instruments and robots that are flexible instead of being rigid. So talks about natural orifice transluminal endoscopic surgery, or node surgery in short, no incision going through the natural orifices like mouse, or creating more dexterity, flexibility while they are basically going through a minimally invasive procedure. So instead of rigid tools that you can just pivot through the entry point, now you have dexterous tools, flexible tools that they can actuate. They are like a snake-like. So we call them continuum robots, or like basically robots that have infinite degree of freedom. So most of the time they are cable-driven, actuated with some indirect actuation mechanism. So since you want to make the robot fully flexible, you cannot put motors there. So the anatomy should be flexible. So one cool mechanism would be cables. So on the bottom right, you see another company actually acquired by Johnson & Johnson in 2020 named Oris. They have made this robotic catheteric system to go through the lung, like to 1 millimeter area inside the lung, and do biopsy. Before that, no surgeon could do it. So, but if you check here, if you check all the literature and industry, most of these flexible tools have been developed for soft tissue interventions mainly. And it's like somehow obvious, because these robots are flexible as soon as they interact. Basically, they are flexible, the body, because they want to create like safe interaction between the robot and environment. But you can't see flexible robots that are being used in orthopedics. And the reason is critical, and it's like very obvious, because you're using a flexible tool on hard tissue. As soon as they touch, they might buckle, and then they don't do what they want. So that's a gap over there. Another milestone that we are working, all of you are talking through the day about autonomy, but that's industrial robotics. But in surgery, what we see in 20, 30 years, we can share part of the task with the surgeon. So semi-autonomous or shared autonomy, that's the topic that we are talking about. But the challenge is that, before talking about challenges, if you're talking about hard tissue on top right, 1990, this is the RoboDoc robots, very first surgical robot built in the world. They have done this on total knee surgery. And it's obvious, it's totally machining, right? You can take MRI, CT scan, you can plan, it's like pretty much command the robot, go and cut. But if you're talking about a deformable tissue, it's super challenging, right? Inside the body. you are talking about a tissue and environment. As soon as you touch, it might deform in a way that makes it very, very challenging. So autonomy on hard tissue is easy, but on soft tissue, super challenging. So we bring it to this nice table or graph that I made. X-axis is dexterity, Y-axis is autonomy. So hard tissue related surgery, they are very easy in terms of autonomy. In terms of dexterity, super challenging. So lower top left, basically quadrant, bottom right is soft tissue related surgeries. We have a lot of actually robots, even like commercialized, but in terms of autonomy, they are super challenging. But ideally, we want to be on top right quadrant. So having robots and algorithms to be implemented on soft and hard tissue surgeries and being robust. So that's the area that my lab, hopefully, we are focusing on. So to do that, we need to develop flexible robots, even sensors and algorithms to be used on both hard tissue and soft tissue related surgeries. So today I want to talk about one of the actually projects, luckily funded by NIH, which is building this image-guided robot-assisted procedure for neurosurgical application. You can see here we have a robotic arm positioning a flexible robot or continuum robot. We call it a steerable drilling robot because instead of just getting in straight trajectory, like all the drills that you have seen, we can control it to go through curved trajectories. It provides a lot of actually benefits for the surgeons because you can avoid anatomy, you can drill in a specific trajectory, so on and so forth. But the challenge is that if you are talking about a flexible robot, you need to be able to track it in a minimally invasive way. So we are also developing flexible optical shape sensors that you can put through our robot and see them through the process to make sure that they are following the commands that we are giving to them. And the most important part of this project is developing also flexible implants. So for the projects that we have, we wanted to treat and improve a spinal fixation on osteoporotic patients. And for osteoporotic patients, what happens, their bone doesn't have the density of healthy patients. And what happens if you have a screw, like typical screws that they are using in various spinal application, they implant a screw into the bone to basically lock 2-3 levels of vertebrae. But what happens? Because their bones are osteoporotic, after some time, they are calling it pull out or loosening, and they need to go another intervention, so it's super hard and challenging. In which what we suggested, we said, okay, let's take quantitative CT scans of a patient. Quantitative means that you can map the bone density in 3D. So we run finite element analysis, we find the regions in the bone which has higher density, and we say, instead of just using rigid screws, that you are limited with the anatomy of the basically spine, basically this line, you can curve into literally any place inside the basically vertebra, drill it with a steerable drilling robot, and then put a flexible implant through. So that's the whole concept. So pretty much this project has biomechanics, finite element, design of new flexible implant, and also a steerable drilling robot. So it starts with actually very, very mathematical model. So I don't want to get into that, but continuum robots and soft robotics to design a good robot to be able to work. We call it holistic design, meaning that we need to consider at the very first step everything, even if you want to control it from the biocompatibility and everything, considering the modeling. So we have developed this like general model to make sure that we can make robots that's working. So we had 4 papers on it. I'm going to skip that, but I want to show you this nice video that actually can be used in soft robotics as well, showing what's the feature of our model is that we can completely model the tension loss and effect of friction, which is critical when you have a cable inside your robot. Super challenging, but pretty much we have modeled it and then evaluated with experiments. Coming back to the definition of problem, what happens in osteoporosis or spinal fixation, they use these rigid screws. But look at here, we try to somehow mark osteoporotic region with different colors with like a high density part of the bone. So you are limited with these straight trajectories. If you are limited and if you have osteoporotic region, no matter what, sooner or later, this screw and fixation is going to fail. So, and you have a screw loosening and pull out. So to address that, we said, let's just design a robot that can curve in and then create a curved trajectory, drilling curved trajectories. So pretty much we have built this robot. So I'm going to show you a few of videos of the experiment. So this is a simulated bone material. We can drill in curved trajectory. It's a thermal camera actually showing, because we wanted to see what's happening through the drilling. And here is I want to just, for the sake of time, just skip that. So this is our drilling live. And then this is actually through the drilling. This thermal camera, since during cutting we generate heat, we can show actually what's happening into. That was by the time we hadn't bought our X-ray machine to see through. So very first experiment. So here are some results showing that very reliably, reasonable amount of time, because if you make something, you hand it into the surgeons, you want to make sure that they are going to use it. If it takes forever, they just throw it out. They are not going to use it. So it's pretty much the same time of cutting. Here is actually a nice video. Not only we can just drill in one trajectory, we call it like branch cutting. In a minimal invasive surgery, it's very important to get in from one hole and then try to minimize and do not compromise healthy bone. So we get into one basic entry point, and you can curve out to different trajectories. So this video shows different channels. We just passed in an endoscope to see actually what's the quality of the cuts. So we did it, and here is actually after buying our fancy X-ray machine here. See, we bought some animal bones. We wanted to test that it's working actually on animal bones. Pretty much we showed that. But then after that, we said, okay, flexible screws. For the first time, we wanted to make some flexible implants. The challenge was that, okay, what should it look like? So we made this half rigid, half flexible implant all through like additive manufacturing using like a stainless steel. It's biocompatible. We designed 2 different versions, but the challenge is that we wanted to know, so you want to have the strengths, you want to have flexibility too. So these are contradictory. So we made different versions, and then we tested under our X-ray. So we created that drill tunnel inside, and we wanted to see if you put it inside the bone, can it create the tabs, basically the drill tunnel, also can it morph inside? Pretty much we could do it. And this nice video actually shows, we wanted to see what happens through the tapping. We had a tiny endoscope inside our cannulated like a screw. We wanted to see actually what's the quality of the tapping, can it morph inside? So we put this tiny camera, and you see actually in the end, I want to show it to you. So to show that we completely can get into, you see that we are waving to the camera from the other side to say that actually this is actually completed and 90-degree care. And you see, I can show you because that's fun. Almost there. You see Sheila, my student over there, inside here, not there, and then she's waving to the camera. That's it too. You see, that's us doing this to the camera, say that actually passed it. Thank you so much. Thanks to the sponsors, and thanks to my students. We're happy to answer questions.
Thank you. All right. Thank you so much. And to any of the speakers, are there any questions that anyone would like to have? We've got time for maybe 1 or 2 questions. Right. If not, going once, going twice, going thrice. Oh. Sounds good.
That's a very good question. So we just finished building this. So that's the next plan that Yash is working on. We have done actually some experiments to see the flexibility and model the stiffness. So we have built that finite element analysis. We have verified it to see, basically the goal here is to design the screw based on the density of the patient, because we have a patient-specific like basically framework. We want to do that, so we have built that finite element model. We have verified it. But next step is to put it into a curved trajectory and add load to see what's the strengths that we are carrying. Yeah, very much. Sure.
Right. All right. Thank you so much. I'm going to hand it over to Yuka and Joydeep.
All right, folks, that concludes all the talks, and thanks for all the amazing talks and discussions. I really see the vibrant discussion conversation. That's the whole point of having TEROS today. All right, so just some quick remarks and to just wrap this up. One is, so for this event, and actually in addition to the co-organizers, Joydeep and Michelle, Ethan, and Josh, and there's actually a group of volunteers helping us behind the scenes. Some of them in this room. Some of them are outside still working. So let's just give them a round of applause and just thanks for them for making sure this event runs smoothly. Of course, and our sponsor, Quincer, has been helping us, like really kind of means a lot. It's like the first time we have this event. And George, if you want to see the
yeah, so never mind that it says 3:30 p.m. We know things got pushed back by half an hour. We're going to have tours going to Anahis Gym. It's going to be a 5-minute walk. Josh here is going to be leading this. So if you're interested in the tour, we'll go from there. But before you go, we have a very important announcement. As a first TEROS event, we'd love to capture this for posterity. So we're going to take a group photograph of everybody here. We're going to go out in the atrium and we're going to take a photograph up from the balcony. Okay. So let's assemble there. Okay, Mitch, you have something to add? Yes, I believe we're going to start from the North Wing gym. We're going to go to the South Wing gym. We're going to go down the stairs to RPL, and then we'll go through the rapid fabrication facilities. Okay. Cool.
Awesome. Yeah, you're gonna see all the amazing robots we show in the slides, right? So those are real ones, like a leg robots, arms, and the surgical robots. Very cool tours to attend. So that concludes TEROS for this year, and I saw that. Thanks for all the feedback, and I saw like a lot of excitement, and I'm gonna follow up with some of you on maybe the future hosting of TEROS, and I think just like Peter said at the beginning, that we are have the intention to make this really a Texas tradition, so not just a one-off event. So thanks for being here, and I know some of you are heading back today. If so, have a nice trip, and some of you are sticking around for the weekend and enjoy Austin, the amazing city. So I hope you have fun. So hopefully we can see you in TEROS next year.
Yep, looking forward to co-organizing TEROS 2023.